Silvia decía, Silvia estaba diciendo algo en el chat.
Sí, que sí habíamos empezado. Hola, hola. ¿Se escucha? Sí, si queréis.
Sí, ahora sí.
Okay. So first of all, welcome everybody to TEFCA. And first of all, I would like to thank you for being here, all of you, both you here in person and people online, because I think this is a really, very important meeting for us, for TEFCA, and in general for the Javalambre Observatory, and this reflects actually the interest that Javalambre, and in particular, in this case, JPCAM, is having for the astronomical community. Of course, let me also thank very especially to the scientific and also the local organizing committees for the huge amount of work that we have done to make this possible. And of course, let me also thank the RIA, the Red Infraestructuras de Astronomía, that of course has made this possible by supporting this meeting. Okay, so yeah, when I was thinking about this meeting, I was looking back in time at the beginning of this project, and of course, when we more than 15 years ago, we were envisioning the Javalambre Observatory and the different telescopes. One of the main goals was to be able to construct a facility, an astronomical facility, that could help to lead and to carry out, let's say, important projects, very big surveys that ultimately could answer questions about fundamental questions of astrophysics and cosmology. And this is, of course, the main goal that we have followed from the beginning. Of course, always driven by, let's say, the JPAS project, that, as you know, was the main driver of JPCAM and the theJST250. But from the beginning, we wanted not only to be particularly focused on JPAS, but also to be able to conduct other projects, okay? So since then, more than 15 years ago, and thanks to a very huge collaborative work from many people, many of you are sitting around here. So now this that originally was a plan, now it's a reality. Now we have the Javalambre Observatory completed. We have the theJST250 operational, JPCAM is taking data, and JPAS has started. Okay, so for us, now we have entered a new, let's say, a new epoch, a new regime in which we are thinking in the future, what's coming next. And this is actually what we are doing here. So the next call for legacy surveys with JPCAM for us is kind of a milestone, okay? Because it's going to allow us not only to improve the scientific return of this facility, of this investment, but for us it's something even more rewarding, the fact that we are going to open the facility and we're going to make it possible to conduct new projects, new ideas, new surveys, and very importantly for us, not only from TEFCA people, but also for a broader scientific community. Okay, so yeah, this is particularly happy for us. I think one of the main characteristics and some things that, at least to me particularly, is very rewarding is to see the huge amount of topics and very different topics that many of you have presented in your letters of intent, that demonstrates that JPCAM and the telescope is a facility able to really conduct a large variety of science, from cosmology, galaxy evolution, stellar populations, Milky Way science, transients, solar system objects, everything. Essentially, almost every topic in cosmology and astrophysics can be conducted from here, from this telescope. And also, very importantly, I want to emphasize the idea that the capability that this telescope has, not only to do the science, but also to think about synergies with other projects that are now hot topics in the scientific community, other projects, other surveys, and other satellites. So I think this is something that we have to take into account. And actually, synergy is one of the topics and the goals of one of the surveys, one of the conferences that we are organizing here in TEFCA, that is going to take part to be held in Teruel in October. We are going to deal with large-scale surveys, and also we want to take the opportunity to honor the contribution of Professor Mariano Moles, that, as you know, he was the person responsible for everything happening here in Teruel and in Jabalambres. So yeah, thank you very much for being here. I wish you a very fruitful meeting. I hope that you can learn and discuss about the technical capabilities of JPCAM. I think that you can really see the feasibility of your projects. Maybe there are synergies with other projects that can really even enrich the idea that you have today. And just to say that, remind that maybe one of these projects may well become the flagship of the Jabalambres surveys in the next years. So yeah, thank you very much. Welcome to Teruel, welcome to TEFCA, and thank you very much for helping us to construct the future of the Jabalambres surveys. Thank you very much. I think now we are moving to the first talk. Right.
Let's start with a very brief introduction and overview of the Jabalambres Observatory. I will just give you a snapshot of the infrastructure that has been developed and is now working at 100% capabilities. And I will give some more details regarding JPCAM and the T250 telescope, just to trigger future presentations and discussions today. So this is the Jabalambres Astrophysical Observatory at a glance. So this is, as many of you know, is a new infrastructure that was conceived to carry out large-scale photometric surveys of the universe. So that implies, or that means that the two main telescopes are very large field of view telescopes with very good image quality, and these are equipped with panoramic instrumentation and very particular or unique sets of filters. So the uniqueness of the telescope's design and the instrumentation and even the observational strategy is the reason why the Jabalambres Astrophysical Observatory was recognized as Spanish unique scientific and technical infrastructure since 2014. So the two telescopes are two out of the three main installations of the ICTS, and these are completed by the data center, the UPAD data center here in the city, that is in charge of receiving the data, analyzing, processing the data, storing, and distributing to the international community. So I will go quickly through presenting and describing the two main telescopes. This is a daytime view of the observatory. Apart from the main domes that you see there, you can actually see the rest of the infrastructure. Of course, apart from the main telescopes, we have sky monitor telescopes in those two buildings. In those two buildings here, see monitor, extinction monitor, and other general infrastructure, control room, clean room, coating chamber, and everything, every single building there is connected through underground tunnels. So I won't go into detail for describing the infrastructure. I think for today it's more interesting if we pay more attention to the telescopes themselves. So this is the Jabalambres Auxiliary Survey Telescope. It's an 80-centimeter aperture telescope with a 2-degree diameter field of view. And you see in that table the main characteristics. I won't stop there. You can take a look later in the presentation because it will be, I understand it will be distributed. This telescope has been conceived and is carrying out the two main surveys led by TEFCA, which are J+ and J-bar. And as an ICTS, we are also offering a minimum of 20% of the time. The real percentage of time that we are offering to the international community is actually much larger than that. and is carrying out since 2021. I don't see the number there. Yeah, 2021 is carrying out also large-scale surveys as part of the open time access to the telescope. In particular, these are the 4 surveys that are being executed with this telescope, together with the TEFCA project J+ and JBAR. So this telescope is equipped with also panoramic camera. You can see in the left-hand side, this circle is showing the telescope focal plane, this 2-degree diameter, and the green square is projecting the actual CCD that is equipped in the T80 camera on the sky. So every single image observes 2 square degrees. You see also in that table, I won't enter into details here. These are the main characteristics of the instrument once it is installed and operating in the Hubble Auxiliary Survey Telescope. Probably the most important thing is that the CCD is a large format CCD 9K by 9K pixel, and the pixel scale is about 0.55 arseconds per pixel. The camera is equipped with a set of 12 filters. This is the J+ filter system. It combines broadband and narrowband, and this filter set has been conceived to perform spectral classification of stars. So the narrowband filters are located are sampling stellar characteristics. And apart from that, we have at the observatory 2 more filter wheels that are equipped with filters that are not J+ filters in order to carry out the surveys, the second generation surveys I mentioned before. So as for today, this is the status of J+. J+ has been observing for several years now. It has completed 5,000 square degrees, and this data release 4 became public last year. So you actually can have access independently of whether you belong to the J+ collaboration or not. This 5,000 square degrees is public, and this plot in the middle, in the bottom middle, is showing the kind of data that we are distributing. So the gray line is a spectrum from a different survey, I think it's Sloan, and it is shown there only for comparison. But the data that J+ is observing are the color points, the photometry. So you see that, for instance, this is H alpha, so how sensitive, for instance, this filter set is to select or to identify and characterize H2 regions. This is just an example of the kind of data that this telescope and this survey is providing. But let me move to the start of the meeting, because this is the telescope that is being offered or will be offered very soon. This is the Hubble Survey Telescope 2.5. Again, you have the main characteristics in the table in the right. It's a 2.55 meter aperture, and the telescope provides a 3-degree diameter field of view with good image quality. And again, this is the telescope that is performing the J+ survey. This is the main survey that we are carrying out now in the Observatorio Astrofísico de Havalambre. Apart from that, we have several memorandum of understanding. I'm showing here the 3 of them, with Hirosita, the team PERS, the JWST, and also with WIB, QSO. And again, as ICTS, we are offering 20% of the time of that telescope to the general community. We started, as Javier mentioned, 1 year ago with shared risk programs plus DVDs, and we are already observing, as we will see later in Javier's talk, some of the programs. But we are here today because we are offering legacy surveys. So these are going to be projects in a 5-year basis. So we expect to release the call very soon. You will have the details later on today. And yeah, this is not the telescope, but the instrument is a non-standard instrument, as we'll see in a second. So I think it is very important to have the opportunity to discuss about potential projects. It is very interesting, the large number and variety of letters of intent that we have received. So I hope that this meeting will give us the opportunity to discuss technicalities and to try to optimize the proposals, the observational strategies, to bring the whole system to the limit to get the highest scientific quality possible of the proposal for the next call for proposal that will be open soon. So here I'm showing in this gray circle is the projection on the sky of the telescope field of view, and with the set of squares of different sizes and colors, I'm projecting here the actual field of view that is observed with JPCam. So you see the moon here, this is just as a reference, just for illustration, never been there. This is M31, this is actually a real image. That was the first live image of the T250 with JPCam. And on the right-hand side, you see a picture of the JPCam cryostat, in which you actually can see the mosaic, the CCD mosaic there, and the actual size of the instrument. So JPCam, very quickly, I will give some details about the JPCam design. I think this is interesting for you to better understand about the observational strategy, the technical constraints and limitation, and also the potential of the instrument. So the JPCam consists on three main subsystems. So here in the right, you see the instrument fully assembled, and in the left-hand side, it is deployed in the three main subsystems that I will show in a second. So the main subsystem is the cryogenic camera subsystem. It holds the focal plane with all the CCDs, the science CCDs. You see the three types of CCDs that the focal plane is integrated in. The science CCDs, again, a mosaic of 14 9K by 9K CCDs. So it's a 1.2 gigabyte focal plane. It is the third largest digital camera in the world so far. And it is equipped with a set of auxiliary CCDs in the field of view periphery to perform image quality and auto-guiding tasks. And also integrates the electronics and all the cryogenics and the vacuum system and so on. The second main subsystem that is important for you to understand is the filter shuttle unit, highlighted here in blue. It holds a magazine with 5 filter trays. Each filter tray integrates 14 scientific filters plus the auxiliary ones in a way that each CCD observes through a different filter. So you have to think about JPCam as a set of 14 different cameras operating all together. And as you probably know, for the J-pass filters, this is the J-pass filter system. It's a set of 56 narrowband, 54 narrowband plus 2 medium band filters in the extremes that are covering in a continuous manner the whole optical spectrum. So the narrowband filters are installed in a way that in each one of the filter trays from T1 to T4, each filter position is occupied by a different filter. This is not the case with filter trays 5 is not represented here, 6 and 7, in which they integrate all the broadband filters. They integrate 14 copies of the same filter. This is important. You will understand it much better later with Javier's talk. And so just to summarize, we have available the J-pass filter system, which are T1 to T4, plus 3 broadband filter trays, G, R, and I. And then the third subsystem is the actuator system, again highlighted here in blue. It holds the cryogenic camera and has the capability of moving with high precision the cryogenic camera, and it is necessary to maintain the optics fully aligned. We have the telescope can move with high accuracy the secondary mirror M2 and also the focal plane. So using images, the focus images taken with these auxiliary CCDs in the border in blue and red, we can reconstruct the aberrations that the system is suffering, and then to compensate the position of the secondary mirror and the focal plane to guarantee the image quality over the whole field of view. Just a comment here, the yellow filters here that you see there, these are for auto-guiding purposes. So as many of you may know, the auto-guiding has not been commissioned yet. So it's not working, and it won't be working at the beginning of the observations of the legacy surveys. We expect to commission during the length of the survey. So that is important to know because that imposes some limitations in the maximum exposure time that is now offered. So with this strategy, of analyzing aberrations and compensating field telescope secondary mirror and focal plane, we can guarantee the numbers are very small here, but this is an image showing that this is the full width and maximum of the PSF. So showing that in that image, broadband image, the full width and maximum is about 0.3, 0.4 over the whole field of view. So this is not a representative image, so the scene was extraordinary that night, but it is very important from the technical point of view because that demonstrates that the image quality capabilities of the telescope camera plus the image quality control loop is operating in an optimum manner. So this is the kind of data that JPass is producing very quickly. So for every single object in the image, we provide the points that are in color here. Again, the gray line is a spectrum from a different survey that is shown there as a reference. So at the end, JPass is providing a low resolution spectrum of every pixel of the observed sky. And there is some data that is already public. So if you are not part of the JPass configuration and you want to access data, we have the early data release one that is public since the end of 2024. And this is the current status of the JPass progress. So we are observing JPass starting in 6 different seeds in order to have objects to observe during the whole year. And you see there the progress of the broadband filter tray. So as you will see later, the progress is different depending on the filter that we are paying attention to. So current status is that we have now observed about 150 square degrees with all the 56 JPass filters. So this data is complete for 150 square degrees. So this is actually a huge amount of data and a huge amount of information. And we have observed a range between 350 and 1200 square degrees with a subset of filters. And this data, as mentioned before, is sent to the UPAD data center, which is our third main infrastructure of the ICTS that has storage and processing capabilities, as well as capabilities to distribute the data to the international community. I won't go into the detail, but the UPAD is in charge of receiving the data, analyzing, processing, storing, and distributing to the international community through different tools that have been developed by the UPAD team. I won't go into detail because just after me, we have 2 talks in which they will give some more details regarding the UPAD and the developments that we at TEFCA have been performing. And I go from the beginning. So this is the observatory, fully working, fully operating. And now we are thinking in the future. So in the next few weeks, we will start the call for tenders for the design, manufacture, integration, and commissioning of a new telescope conceived for planetary defense and space debris. This is going to be so this is a concept, and this is generated by the AI, so don't pay attention to that. I was just looking for something to put there. So this is going to be about a 1.5 meter aperture with 20 square degrees. So it's a new jump, a new step in field of view. And again, this is our main project for the future developments here at the observatory. If you have any question or you want to comment anything, then during the coffee break we can comment, and that's it. This is what I wanted to mention. I don't know if you have any questions or we can just discuss later.
Yeah. Sorry, because I didn't introduce you. I was doing other things, but one question.
Yeah, very quick. Nice talk. Thank you. What kind of camera, what kind of instruments are you expecting from?
That's a good question. So the goal in the regular operation of the telescope, we haven't started the design yet, but we are planning, and everything has been designed to integrate a CMOS camera with a mosaic of 2 by 2, so 4 large format CMOS detectors. So it's going to be 4 about 8 or 9K by 8 or 9K CMOS detectors. So, and with this camera, we will cover the 20 square degrees. So 20 square degrees, a little bit more than that, will be the effective field of view observed with the camera. For the first year or years of operation, we will install a camera that we already have that was installed before in the T250, which is the Pathfinder that integrates a single 9K by 9K CCD detector that it will be covering a little bit more than 5 square degrees. So we are moving in phases. Well, we start with the telescope. We will start commissioning of the telescope with the Pathfinder, 5 square degrees, and in parallel, we will be developing the final instrument that will provide the 20 square degrees with a CMOS focal plane.
Okay. So I understand broadband photometry.
Yeah, for planetary defense and space degrees, for sure broadband photometric or very, very broadband photometry. But this telescope will have the potential for carrying out other projects. So depending on what other secondary projects, let's say that way, appear, we may need or we may want to integrate different filters. Yeah, and I'm sure that this telescope will become in the future another main infrastructure of the observatory, so will be offered to the international community at some point.
Thanks.
We may organize a real meeting at that time.
Thank you, Tony. So now is the turn for Silvia Bonori, who is connected online and is going to talk about the scientific highlights in JPass and mini JPass. Hi, Silvia. Good morning.
Hello. Sorry. Hi. Let me share. I don't know why. Okay. Can you? No, you cannot see anything, right? Yet. No. Just give me a second. Then I think I can share, right? According to you, there is no problem, right? Let me try to share with another. That's why I've been connected twice, because I have one computer without camera and another computer that has problem sharing. So maybe between the two I can do something. Yeah. I don't know why I can't. Do you see anything?
No, so in principle the system does allow you to share.
All right.
Otherwise, you can send me the PDF.
Yeah, let's just do that. Oh, that's unfortunate, but okay. Yeah, actually, I don't know if it was a problem because it was a bit difficult to connect. I couldn't connect through the link, but only with the information of so I don't know if there are some constraints on being able to connect. I don't know.
And more people have problem. In principle, there shouldn't be. I don't know if Zoom has introduced some extra.
Okay, presentation. Okay, so I send it to you. One?
Yep.
Okay. So while it's going, I'll try again. Oh no, now you're sharing, so okay. It should have gone there.
You can try. When the mail arrives.
Yeah. Ah, now you see?
Yes.
Okay.
But you are sharing.
It's not full screen, right? Let me try the PDF. Okay. All right. Okay. Well, it's the whole, is it like this fine?
No, it's only half a screen.
This is us. No,
No, this is not us. This is
no,
her screen.
but we cannot change the bandage. Okay.
It's her screen.
Okay.
I cannot share only a selection, so is this fine like this?
No.
Are you sharing the full screen or
Yeah.
just so?
Yeah. Yeah, I cannot choose only
It was almost fine for 1/10 of it.
let me try again. What about this?
No,
Is it better?
no, it is the same.
Okay, then I don't know what to do.
For us, online works.
Yeah, I also see online because I'm connected twice and it seems okay. But as you wish.
Maybe you can send the presentation to the.
I did. I should have it. So if you prefer, I stop and you share it.
No, Silvia, send the presentation by email and we
I did. It's already issue. They should have got it.
But in the meantime, we will have Hector Vázquez talk.
I see that.
Because if not, but do you have your talk? Okay. So, okay, we will, Silvia, we will watch the Hector's talk before yours.
Okay.
It's okay with you because you needed to leave, I remember.
Yeah, and at 10:30 I need to go. That's actually the reason I cannot be there because we have an important meeting here going on. So
Okay, we have time.
Yeah.
Okay. So Hector is going to be about the observatory data processing. Thank you, Hector.
Thanks. So, hello everyone. I am going to talk about the details on the data processing. JPCAM is a complex instrument, so I realized that some of the details of the observational strategy and the camera maybe have not been put on the table yet. So this may be a little bit dense at this talk, but let's try. So here is the team. This is the Departamento de Desarrollo y Archivo de Datos. These are the people that is in charge of coping with the OAJ data. We are using, since 2010, we developed a pipeline to actually reduce the images from the two main telescopes. This is called JIP. This is mainly implemented in Python. And more recently, we are also including some modules from Nuestro suite. Okay, so as I said, our purpose is to provide the optimal processing of the images for JPAS, in particular for JPCAM. And depending on the strategy that you are using for observing, we will be able to do different processing of the data. Okay, this is just a sketch of the what you can see the flow chart of the pipeline. I will go into the different steps now, the most relevant ones lead to JPCAM. But mainly you can see here that I split the data flow into columns. The first column is what we expect to be able to provide for any kind of observations. Using our imagination, in principle, we think we can provide this for sure. And the other column is for the case that you are using in your observational strategy a differing step between your individual exposures. so creating some overlap between the individual exposures, and that will allow us to perform additional steps in the processing. This is something to be discussed case by case because every project may have different characteristics, but in principle, if that exists, we may be able to. So let's dive into it. Every CCD of JPCAM has, as you can see in this image, has 16 amplifier regions. These are regions where the CCD is red, so you have different noise, let's say, readout noise. And each CCD has also some virtual pixels that are read after the reading the exposed area. That is the post-scan regions. And this is what we use in order to correct from the bias level. Okay, so we are using this region that is not exposed to estimate the profiles in both directions, in the horizontal one and the vertical one for each amplifier on Skype images. So this is the way we make this correction. Another very important correction that we recently implemented, and now I am just explaining that is the standard way to proceed, but this takes a lot of time, is that at some point we realized that the camera seems to have some non-linearity at low counts. So this is something that we need to model. I have no time to go into the details, but the takeaway message is that we are able to model this behavior using DOM flats without the filter. You don't need to worry about that because we are going to take care of this. So we are going to have these master frames for the correction, and this correction is made pixel by pixel. So depending on the flux of each pixel, the correction is applied according to this master frame. Okay, that we model. As in order to show you how this works, this is an input image. This is the correction that we derive from the flats, and this is the output. As you can see, all these vertical features that you can see here are disappeared when we apply this procedure. Okay, so again, you don't need to worry about that. This is right. This is a standard processing. I can tell now. I take advantage of this image. This is an untrimmed image. You can see that there is some vignetting along the borders of the CCD. This is made by design. We need to baffle the borders of the filters in order to avoid spurious reflections of stars to the borders of the filters. This is like a plastic frame around the filter. So at the end of the day, we define the region of 5% vignetting. This is a fixed rectangle for each CCD, optimized, and we trim the images. Again, something that we can always do. And this is not in order, but the astrometric calibration is done using IATF. The flat fields are made. The flat fielding is corrected using twilight flat fields, as usual. Nothing special in this case. And then let me go into one of the, let's say, optional reduction steps. This is the super background correction that actually requires a first step, which is the source masking. So what we need to do is to identify all the sources in the image and actually mask of them in order to model the background of the image. This is something that we can always do on individual images. So what we do is to use, well, beyond masking bad pixels and bad columns, what we do is to, you can see an example here, you have an input image, we run extractor, we get the segmentation of the image, we dilute it, we make larger all that segmentation map. And then we also include external catalogs for both stars and galaxies. You can see some cases here. And the goal is to mask any source that is known from our image and from outside catalogs. Because what we are interested in is on the background signal that we have in the regions where we are not masking anything. This is important that this mask can be done always, but the next step, which is actually building this super background image, which is this one, without no sources. This is something that your observational strategy, depending on what is your observational strategy, can be done or not. Because in order to do this effectively, we need some dithering between exposures. You can see here the procedure. We identify a group of images with the same or similar background features. We use the masks that I described before. So we get rid of sources, and we combined the resulting image to get this master super background image for this group of images. And you can see here how this works. So we have this input individual image. We use this super background. We scale it according to this image, input image, and then we subtract the background. So this is only, the limitations of this procedure is that we need some dithering, because if not, all the sources are always at the same position. So you don't have information that you have a source. You do this processing. The other limitation is that if we are coping with very dense fields, everything, or most of the area is masked for all our sources. And we also need a sample of similar backgrounds, images, to actually be able to create this super background. So this step is optional. So it will depend on your project. We can do it. And by the way, any background feature that you can have in the image, if you stack the images, you will find funny patterns in your stacked image, of course. Let me talk about, maybe you have noticed that there are some background features that you may not be familiar with. This mostly happens with trait 4, which is the trait with the reddest filters. And this is a feature of the camera. And for those filters, you can see that the ones in the periphery, we can see different radial background patterns that are, it is a feature of the cam at those wavelengths. So this is why it is needed to, if your site requires that, it is needed to do this process to correct from that. And this is for illustrating how this works. You have the input image. In this case, it's not trimmed yet. Here we have the image trimmed, and then you get the final result. Okay. For the bluest filters, you don't have these strong patterns. Okay. This method works both for these patterns. It also works for fringing. In the case we have fringing, with the same procedure, we actually correct from the fringing. And if we have some gradient because of the moon, that is more cumbersome because this may change with time. This can also may work for correcting for that. Okay. Photometric calibration. We can provide photometrically calibrated images and catalogs. And our standard way to do that is to use the best catalog from Chiao and collaborators. This is a catalog based on, it has as input the Gaia spectra, and they use different sets of transmission codes of different photometric systems and standard photometric calibrated stars to provide like an improved catalog, in particular in our case in J+ ones. So this photometric calibration can be made for J+ filters and also GR. Therefore, in case you are using another filters, we don't have this information, so this needs part of it. Okay. This photometric calibration is also used in order to assess something that is also characteristic from our telescopes and cameras, which is something that is needed, is the so-called illumination correction. This happens with telescopes and instruments with large field of view and with field correctors. This is often happens. And the feature that we observe is that when you look at the flat field corrected images, you can notice that there is a photometric bias across the CCD that is systematic. So in order to correct from this problem that comes from the application of the flat field, because there are some concentrations of light, I cannot go into the details, but we know well this feature. We take advantage of the photometric calibration because we use this catalog. And for every individual image, we get a 0 point, a single value. But then you can measure the residuals of the photometric calibration across the image, and you get this information of the residuals in 2D. We stack a lot of these residuals, and we have this type of image. This is for play 5, which is I-band. All filters are I-band. And then we model them with Chebyshev polynomials, and we correct from these biases. So in the end, we have a flat photometry across the CCD. That's the final message. We take care about that. You don't need to worry about that if you are using JPass filters and or GRML. An extra fine-tuning of the photometric calibration is, in this case, optional. It will depend on your observational strategy. If you are, I'm showing here the strategy of JPass. This is how we observe. We make 4 ditherings. So we have 4 different images, let's say, with large steps. So doing that, we manage to have the same objects observed in different positions of the CCD. Taking advantage of this dithering, we are able to optimize a 0 point offset for each filter. So we minimize the photometric precision of each filter. So you can see here in this plot what is the initial precision of the calibration in black. And after applying this homogenization using the overlapping area, using the same objects, observing different images, we are able to reduce the photometric precision to these 2.5 millimagnitudes. This is the case for JPass. This is the improvement factor of the 2. And this can only be made if we have a large dithering. If we don't have it, we cannot do it. And in that case, you will have the initial photometry. And another aspect of the data is that when we finalize the photometric calibration, we flux calibrate the images, both the individual images and the static images. So to arbitrary 0 point of 25. So this means that you can measure on your image straightforward and get the calibrated photometry from the images because they are already calibrated. Okay. Another aspect we are providing in terms of the different photometry that we are providing, we also offer the aperture correction. For any of you that are not familiar with that, this means that, for instance, if you are using 3 aperture in diameter aperture, you can see here for every curve is an object, and you can see how the photography depends on the aperture that you are using. So this is the magnitude that you get for this limited aperture. And if you compare that to the total flux that you will get, and we use as a proxy a very large aperture, there is a difference that we estimate on each individual image using high signal-to-noise stars. And then we assume that this is the ending flux that you are losing when using this aperture. So this is done for 3, 6, and 1.5 arc seconds, and we provide this photometry. This photometry is aperture corrected photometries. And I'm finishing. I'm reaching the end. This is another aspect. This is how we translate these aperture corrections to the stacked image, and this helped me to introduce something that we will talk across the meeting, I guess, that if you are proposing a survey with JPCam, most probably you will face similar situations as in JPass. And this means that if you want to make a stacked image of your project, most probably in the area that you are making the quad, that would be this one, you will have a mixture of observations made in different lengths. This means that most probably you will have a mixture of PSFs and full maximums. And this impacts on the aperture corrections, because this is going to make a mix of many different properties, and you end up, as you can see in this image, this is how the individual full width maximum is distributed in this area from the individual images. Well, so we have implemented a process that uses the information of the aperture correction on the individual images, and when we combine the images to make the stacking, we also include in this process the aperture correction as an image. We are assuming a flat aperture correction because for each CCD, the field of view is small. So as a first approximation, we assume that this aperture correction is homogeneous. And then we combine and we end up with these maps, which are the aperture correction in the stacked image. And you can see how this works. This is before applying this aperture correction, the distribution, and after applying that, you see that the distribution is more compact. So this seems to work well for 6 and 3 aperture correction. So this again is just to let you know that you will have most probably this issue, the mixture of the PSF, and we managed to cope with that using this procedure. Okay, good. I'm glad I am actually getting into the end. This is like a takeaway, depending on your project, regarding what we can and we cannot do, depending on your observational strategy. And mainly, and basically, the two main points are whether or not you are using JPass or GRI filters, or a new filter, or whether you are using dithering, but a relatively large dithering step in your observational strategy or not. These are the two. So this is JPass filters and dithering, this is new filter and dithering, and this is no filter. So all the green boxes means that we can do it, we can deal with that. And for the super background, if you have dithering, most probably we will be able to make this correction, but we have to see every case. In principle, we are positive about that. And the same for the image stacking. But in the case of the photometry, if you are using new filter, we have to study whether this is doable and how. Photometric calibration of the images. And the most important thing is if you are not applying dithering, the super background correction is not guaranteed, what I explained before, and the photometric calibration of homogenization cannot be done because we don't have it. And the stack images, the stacking of the images will be, in that case, would be studied, let's say, to see if it's possible under what circumstances. No, because if you don't do the super background, then your stacked images may have weird patterns. So this is more or less it, because I will give the floor to. But well, the thing is that we are going to provide calibrated images, flux calibrated images and catalogs with maps and masks for the individual images, as I said. And in case we can make the stack images, according to what I explained since now. This can also be provided. Tamara will discuss, will show us how the data is provided to the research teams and more details. So that is it. Thank you very much.
Thank you, Hector. Questions for Hector? Thank you for the table. The Japanese table is very, very clear.
I have a question. Sorry, I have no voice. Oh, perfect.
Fine.
So you mentioned that if the field is very crowded, then probably the super background subtraction will fail, right?
We have to see at what level
Exactly, that was my
the
question.
crowding is. But this is just to, we really don't know. We haven't tried. But this is just a note of caution about these characteristics of the image. You know that JPass is not that is not pointing to very profile, so we don't have experience of that. But as you can see, it can limit and impact this procedure. For that, we need to make some tests.
My question was more into that direction, whether you have tried some crowded field and you know what is the limiting density of stars or something like that.
It is something that we could explore because we already have some crowded fields already. We can study that so we can provide precise figures.
Yeah.
There are no more questions. Let's thank Hector again. And now we return back to Silvia Bonoli's talk.
Silvia, do you want to try sharing now from the navigator?
Oh,
Yes.
Nice. Perfect.
Yeah, thank you.
Nice.
Now it works. Okay, sorry about that.
So when you want, Silvia, thank you.
Yeah, sorry. And I'll try to be quick. Well, I guess I can skip all the technical part, given that also Tony and Hector already talked about it, and also apologies for not being there. All right, so I just wanted to give some highlights of the science that has already been done with JPass and also mini JPass and JNEP, the precursors of JPass. So I'm sorry, let me see. Okay. All right, so, well, we already discussed that JPass is a large spectrophotometric survey of the northern sky. It's a Spanish and Brazilian collaboration. Very quickly, it relies on this beautiful set of filters, and they were designed precisely to get a very accurate photo Z with a target precision of 0.3%. Primarily with the idea of doing cosmology, so the large-scale structure, study the large-scale structure of the universe. But as you will see with this very beautiful set of filters, there is a lot of science that can be done. So, well, I don't have to say anything about the observatory, nor of the camera, how JPCam compares to the T80. I think briefly just saying that, well, with this large field of view, we can cover large areas of the sky, which is really the goal of this wide field survey. And this is where we stand at the moment. On the left, it's with all the filter, what's the coverage? About 150 square degrees, as also Tony said earlier, centered around 6 seats across the northern sky that allow us to cover some areas in each moment of the year. And in the right is just an overview of what is the area covered just with one filter, with tray 1, just to give an idea that within an individual filter, the coverage is much larger. So on the public side, we have this early data release that was already a year ago made public, about 12 square degrees with all the filter, but there is more data available with a subset of filters, and also the extended early data release that will become public at the end of this year. It will be about 30 square degree with all the filters, but again with a large subset, with a large ancillary data with a subset of filter. And more data available, of course, to the collaboration to do science in a wider area. But, well, these are some information about the EDR, the public data release. On the right, you see the footprint centered on the seed of mini-JPass. On the top and below, around another area, the science verification, what we call the science verification area for JPass. On the left, you see on top the magnitude depth for the filters, which is always between 21.5 and 22.5, depending on the wavelength. And also on the bottom left, the full width of maximum of the PSF, which is also changes with filters, but it's always around between 1 and 1.4 at worst. So before JPCam, we had a camera, what we call the Pathfinder camera, which was just one CCD centered at the center of the focal plane, which was 0.27 square degrees, but with the same pixel characteristic as JPCam. And this allowed us to take data that really was key for the JPass collaboration to do first science. And there were two main fields that were observed with all the filters. One was the AGIS field, what we call the mini-JPass field, and the other one was JNEP on the north ecliptic pole. And together with these two data sets, it's where really we started pushing the science within JPass. About mini-JPass, well, this I will go very quickly. It has similar depth as the one of the EDR, although it was less homogeneous as the current new data release. These are just some example of stars as observed with mini-JPass. And we started, starting from the small scales. Already there have been a few works analyzing stellar properties, although the sample of stars is quite limited, so there isn't yet much that could have been done with the stellar in the stellar fields, but there is much more coming up soon. So metallicity, temperature properties of white dwarfs. So there is already still a variety of analysis that has been done. If we move to galaxies, these are examples of galaxies and quasars going from lower redshift to the highest redshift, one of the highest redshift, a quasar in the bottom right at redshift 4.2. You see the beautiful broad emission lines of the quasars. So about, with this very accurate, let's say, spectrophotometry, we tested, first of all, the photometric redshift accuracy. Most of the work has been led by Antonio Hernan Caballero. Developed a few specific packages to really optimize the photo-Z with JPass data. And indeed, down to a magnitude of 21.5, 22, we have the more than half of the sources, more than half of the galaxies reach indeed the target precision for cosmological study, but also for a lot of extragalactic science. This is an example that we showed for mini-JPass, how it compares just with a qualitative view. This is the coordinate, right ascension versus redshift. The points indicate the redshift position, the space and redshift position of these galaxies. In blue, it's spectroscopic data. In yellow, it's mini-JPass. And you see that there is a very, very good match. At least this is a qualitative, but you can see right away there is a very good match up to redshift for about 0.6, 0.7, where then it starts becoming difficult also because of the depth of the survey. So again, going from, let's say, lower redshift to higher redshift and cosmology, there have been already several working on taking JPass as an IFU, a low resolution IFU, Julio Rodriguez Martinez done a couple of work and developed a software, specific software that analyzed the spatial properties of galaxies. Here is a recent work from Escandarlu et al. 2026 on studying the tidal features, the stellar properties, the stellar population properties of the tidal feature of emerging galaxies. Here on the left, we have an analysis of the spatial variation of the star formation rate in galaxies with an AGN, with an X-ray AGN, and without an X-ray AGN to study the effect of AGN in the quenching of star formation of galaxies. Going to more the galaxy population as a whole, Rosa González Delgado has pushed a lot of work in studying global properties of galaxies. This is, for example, a color mass relation. Luis from Granada also studied the evolution of the mass and the luminosity function up to redshift 0.7. Emission line galaxies are really one of the key kind of objects that can be studied with JPass, because with the narrow filter we can really select emission lines and also not only find them but also characterize their properties, like the flux, the equivalent width. A lot of work has been done here, for example, at lower redshift. Ginés Martínez Solaeche has done several works and developed a new code called Ojalá that characterizes objects and emission line galaxies. Also, Onti there has developed a very nice Jolines, another very nice software to characterize nebular lines. There have been also several works on extreme emission line galaxies, so galaxies that have a very weak continuum or non-existing continuum with very strong emission lines. So these are some examples of galaxies that have been detected up to redshift 1. And even going to higher redshift, there's been quite some work on Lyman alpha galaxies, both on diffuse emission. This work was primarily pushed by Rana. These are, for example, the Lyman alpha diffuse emission around quasars at redshift, and I forgot exactly, it was around redshift, between 2 and 3. And this is Lyman alpha luminosity function from, this is from mini JPass, but now with the wider area, there is a lot that can be done to constrain this better, the Lyman alpha luminosity function across redshift, up to redshift 4 or 5 even. There has been quite a lot of work on quasars to detect them, to find targets, also for follow-up study from the WIV QSO survey, which will follow up a large fraction of the quasars detected by JPass. And there has also been a couple of analyses on the potential of using this spectrophotometry to even characterize black hole masses by taking advantage of an estimate of the emission line of the quasars as detected by JPass. So moving to clusters, thanks to the very high redshift, photometric redshift photometry, cluster finding has been tested to be quite efficient. There have been a couple of works from Matteo Maturi with the code Amico, and also from the PSZ-WAV cluster finder from Dubrava et al. And just to give an example, here, just to let's focus here. For example, these are some. This is the, let's say, the strength of the amplitude of the cluster detection versus the mass of the cluster. And this is in units on 10 to the 14 solar masses. So 0.1 means 10 to the 13. So this is group mass. So this implies that JPass, thanks to the high photometric redshift accuracy of the galaxy, can detect clusters. Sorry, there is some noise here. Clusters down to the group mass. And this is interesting, the overlap with the German part of Eurosita, that, you know, it is still the overlap in terms of area is not very large yet, but it will become large as we progress with observation, and it will be interesting to combine X-ray and optical data. well, having also characterization of clusters and group, it allows the JPass collaboration to also study the galaxies and their environment. And again, there have been some work from Julio Rodriguez Martin and also Rosa on the galaxy properties as a function of environment, but also characterize also filaments and the connectivity, so like the connection between galaxy properties that are in the same large-scale context, large-scale view from Daniela Galarraga Espinosa. So with this, I wrap up. So, well, we already heard about JPass, and I'm sure all of you know about it, this large spectrophotometric survey, which whose features are really this beautiful set of filter tray. And now within the collaboration, we had already quite a large amount of data to start the science, to at least prove the capability of JPass. And now that we have much wider area, that's really where the use of JPass is starting to really flourish. And indeed, to date, now we have about 50 papers with more than 700 citations. And then with the new 100, we are really eager to get the new internal data release of 150 square degree to really push this to really the big data era. Yeah, thanks.
Thanks, Silvia. Questions for Silvia? Online? If not, we thank...
There is a question online, Javier. Sorry.
So, go ahead.
Yeah, sorry. Thank you, Silvia. Yes, so I have a question. So for the full plan of the JPass coverage, the footprint, do you consider to cover any void?
Any void? Yeah,
Yes.
yeah. So, well, I didn't indeed spend much time. Okay, this is here. So, I mean, JPass in principle, the target is to get to thousands of square degrees. So the initial goal was 8,500 square degrees, which will take quite some time. But we hope to get to, within the next couple of years, to get to 1,000 or 2,000 square degrees. And indeed, there will be many voids there. So any science also with voids would be quite interesting. Sorry.
Yeah,
There's
no
been
problem.
already some work about void characterization with the photosys of JPass. So maybe I can send you the reference.
Yeah, that would be helpful.
Yeah, I haven't mentioned this here. Yeah.
Yeah, thank you.
Welcome.
We thank Silvia Bonoli again. And now is the turn for Tamara Tibera, and she's going to talk about the data delivered and data access for the data from the observatory. Thank you, Tamara.
So good morning, my name is Tamara Tibera, I'm a scientific database engineer at TEFCA, and I'm going to present the infrastructure currently available at the Observatorio Astrophysical de Java del Hambre for data delivery and data access, focusing on TAC data and TEFCA catalog portals. The observatory has its own complete infrastructure covering from daily data delivery to science-ready data products and publication. On one side, we have the TAC data portal, which provides access to the survey images and products generated daily during the observation and processing phases. It includes raw images and processed images and products. On the other side, we have the TEFCA catalogs portal, which provides access to science-ready data delivered in curated data releases, which includes processed images and catalogs. So TAC Data Portal is a web portal which provides access to all survey data products generated daily on the observatory. The products available on this platform are raw science and calibration images like bias, flash, processed individual images and associated products like catalogs, and the master frames used during the data reduction process. In this portal, that data is ingested continuously, normally every day, but if a higher frequency ingestion is needed, depending on the requirements of the project, is also available. When new data is available in the TAC data portal, an email is sent to the full project team indicating the newly available images and products, and also the full survey team has access to all the data through this web platform. Currently, we are offering through this web page portal the data of more than 190 different projects observed with the different telescopes and instruments that we have in the observatory. It implies that we are offering more than 280,000 of raw science images, and we are also offering more than 250,000 of processed individual images. The portal provides different services to search, explore, and download survey images and products through a web interface. And now I want to briefly show you how this interface looks like. So, just a moment. So this is the home page of this portal. In this home page, the different projects to which the user has access are displayed. And I am interested on JR's data access. So you can go directly to that. Here. Okay. Well, it takes a bit to load the data, so I have loaded it here. As I have just mentioned, this portal offers raw images, reduced images, as well as master frames images. So in the portal, we have a different tab for each type of image. Here you can see here you can see in this table the different reduced images available for this project. And for each image, we have different information like the coordinates, the filter with which have been observed, and more information like the exposition time, mass. All this data can be directly downloaded in a CSV file using this service. Just download all into CSV, and with that you can work with the data in your own scripts or in your computer instead of having it only in the web. Another important feature of this portal is that the data in the table can be filtered. So imagine you are only interested in the images of one filter. So here you can select the filter, for example, display all. I am interested only in the images observed with that filter. So here you go, apply filters. And now in the table, only the images observed with that filter are displayed. For each type of image, we are offering different images and products. So in the case of reduced images, the full fit image is always available here. The catalog generated using the extractor is also here. And the different products can be also downloaded using this icon. If you are interested in more than one catalog or more than one image, you don't have to click on each icon one by one. You can, for example, select the ones you are interested. For example, in this case, I'm interested in these four, the images and the catalogs of these two images, and you can generate a download script for the selected files using external tools like wget or CARD. And in the script, you have the instructions to use that scripts. And the same if you want to directly download all the files using these external tools. And for the rest of the rest of the images is similar. The interface is the same. So here you can see the different raw images, the calibration images, as well as the science images, raw images, and yeah, the interface is very, very similar. So in addition, programmatic access APIs are currently under design and development. So in the near future, they can be also available to access to all this data, to all these images, catalogs, and products in an automatic programmatic way. The other part of our data access infrastructure is the TEFCA Catalogs portal. This portal provides access to science-ready data releases. It is important to keep in mind that this type of publication depends on project-specific requirements and is evaluated on a case-by-case basis. A data release normally contains reduced individual images and quadric images, as well as survey tabular data products, normally catalogs. One important thing here is the data is ingested only one time when a data release is published. And the goal of this portal is to provide access to the data release data to the wider community. We are currently offering the data of 14 different data releases, and 2 of these data releases are for the theJST250 legacy service. The TEFCA Catalogs portal provides advanced tools for data search, visualization, and download. It's suited to a particular need. We are offering the data through web interface services like a Sky Navigator or services to search, visualize, and download a set of objects or a set of images. And also, all the data is available through virtual observatory services, which are international standard services to access the data defined by the ABOI. And all our virtual observatory services are also published through our TEFCA Publishing Registry to make them discoverable and accessible into the virtual observatory ecosystem. So now I want to show briefly how this portal looks like. So this is the homepage of the TEFCA Catalogs portal. In the homepage, the different data releases are displayed. In this case, you can see, for example, the J+DR4 and also JPass early data release. So you can go to one of them. And when you go into one of the different data releases, you can see the list of services available for that data release. The services as well as the data provided for a data release can be different depending on the data release. So in that case, for example, this is the list of services, but if you go to another data release, maybe the services are different or the data model is different, or also the products provided by this portal can be also different. So in the case of EDR, the JPass EDR, I want to show you this service. This is one service that allows you to navigate through the sky, through the JPass color images. So you can zoom in, zoom out, navigate, move from the sky. One important feature of this portal is that all the services are highly configurable. So imagine in this case, the cycles display corresponds to the red ones are galaxies, the blue ones are stars. But if you want to change the threshold to differentiate between galaxy and star, you can change it, or you can add conditions and only display the object that applies that to which applies that condition. So all the services are very, very configurable. And if you are interested on one of the objects, for example, this one, you can go directly to other service, which is the Explore object, and see all information available for that object. Other important feature is that all the different services are interconnected within them. So imagine you want to see the quad images in which this object has been detected. You can go directly to the quad image search service. And here you have the list of these images where this object has been detected. Or imagine you are interested on the reduced individual images that compose these quad images. You can go to them, clicking here, and here you have the reduced images that compose that quad image or stack image. Another important feature of the portal is that it is also interconnected with external tools biocompatible. That means that if you are interested to work with that image, for example, in Aladdin or another external tool, you can directly send the image to the external tool. And you don't have to download it and then load in the other tool. So imagine you have opened Aladdin and you want to work with this image in Aladdin, you go direct, you click here and you access. And now the image is being loaded directly in Aladdin and you can start to work with the fit image in this instrument. So there are a lot of different services. I don't have time to show you all the different services. There is a good manual there where the different services are explained with the different configuration options. You can download it by clicking here. So you can, if you are interested to know more about any of the services, you can see the manual. And another important point is that the data is not only available on the web interface services, it's also available through bio services. So here we have the information about them. These are services which are standard. They follow the protocols defined by the International Virtual Observatory Alliance. So you, with these protocols, you can access to the data through external tools like Topcat, Aladdin, or you can access to the data in your own scripts, using, for example, libraries like PyView. Now we are offering the data through the CIAP, concert, and TAG protocols. That means that to access to the images, we are using CIAP protocol, Simple Image Access Protocol, that allows you to search for specific images in our data releases and to retrieve the full images or the cutouts of the images in a standardized way. And also the catalogs are available through the Simple Concert that allows you to search for specific objects in a region, in a concert region. Or also all the data is available through Table Access Protocol that is a very flexible and powerful way to access to the data because it allows you to retrieve and to search the data directly in our databases using a language which is also standard, which name is EDIQL. Now I want to show you, instead of JPass EDR, another example, which is Mudehar DR1. Mudehar is one of the JST250 legacy surveys. So in this case, you can see that the list of services is different and in that case, it was decided to offer the data only through bio services. In that case, the data is offered through Simple Concert to search the objects of the catalog provided by the research team. And also, all the data can be accessible through Table Access Protocol. Another important service is that if you want to query directly our database using EDIQL and TAG protocol, we provide also a web interface, which is Biosynchronous Query. And in this web interface, you can create your queries. So in this case, instead of, for example, I want to obtain the data from this table, validate the query, run the query, run it, and here you have the result of the query. You can download it. In that case, in a CSV, but you can download the information in different formats like FIT, CSV, TSV, Potable, which is also defined by the Virtual Observatory Alliance. Or you can visualize the results here. But for example, here you have the different results. Another important feature is that when we are offering the data through that service, we always provide this service, which is ethic well held, in which a few ethic well tips are displayed. And also, this is very important, for each data release, we provide a set of examples that are specific for that data release to obtain the most common, or to query the most common, or to run the most common queries. And also another important thing is that for all the different tables that compose the data release, a help is also given. So in this case, for example, for this table sources, the table description is here, and also all the different columns available are displayed in this service. All this information is provided by the research team, and for each column, a description is also provided and also displayed, as well as the units in a standardized way, defined by the Virtual Observatory also, and also the unified content descriptors, which defines also in a standardized way, which what that column is offering. For example, imagine for the coordinates, with this UCD, you can directly know that this column is offering the coordinates, these two columns are offering the coordinates. Another important thing that I have just previously mentioned is that all our bio services are published through our THEFCA publishing registry. That means that we are making them discoverable and accessible through the Virtual Observatory ecosystem. That means that if you go to a standard tool, in this case Aladdin, you can directly search for the data release. In this case, Mudejar, and here you have Mudejar data, and you can directly use Mudejar data in the tool. In this case, this is for to execute a concert, or you can execute a tab query if you click here. And now I want to show you how it works, for example, for a concert. Give me 1 second to copy the coordinates. So you click here the coordinates, load that. I'm going to repeat. Okay. So let's something is present. And number one, but yeah. Normally you can see here the objects found in that concert. I don't know why today is I'm afraid. So. So to finalize and to summarize, the OAJ data infrastructure is composed by two different data access layers. One of them is Tag Data Portal. Tag Data Portal provides continuous access to observe and process survey data. This portal it will be available for all OAJ second generation surveys, and it provides raw and reduced data products. And on the other hand, the THEFCA Catalog portal provides science-ready data releases. This type of publication is subject to project-specific evaluation and requirements, and the different services, data provided, and data model has to be discussed between the research teams and CEFCA, and it can provide tabular data products like catalogs or reduced and quality images. In short, our goal is to provide a complete infrastructure to access future second-generation surveys data. Thank you for your attention.
Thank you, Tamara. Questions for Tamara? Online? If not, I thank a lot all of the speakers and all of the work we and you have done to be to be ready for this opportunity that we give the community. Okay, so thank you. Now I have two announcements. The first is that we are going to take the picture of the meeting here with online people. So online people, please put your camera and we can do the picture. So come here. Please.
Give the second one.
And well, the second one is, remember that this should be returned tomorrow after the meetings. Put them in the table, on the table that it's outside, please.
Aquí, al lado de Rosa. Donde nos ponemos.
Javier Miguel, sí, Miguel. Miguel, sí. I'm your boss.
Aquí hay sitio.
Yo lo intenté.
Estamos.
¿Así?
Javi va a salir con la cara naranja.
Joder, es que...
Está cantando la respiración.
That's okay.
Me quedo ciego.
We come back in 25 minutes. So 11 past 10 for the people also online. ¿Sí? Vamos a café. Jamón, no lo sé. Creo que jamón sin alcohol, pero... Sí, no sé qué está aquí.
¿El jamón sin alcohol?
Sí, verdad. Well, I guess we should start again. Now is my turn, and I'm going to talk about the future call for proposals with JPCAM, the observing strategies, and also the tools we have developed to execute observations with JPCAM. Well, my name is Javier Zaragoza, and I'm the head of the scientific operation department in the observatory. So the observations are executed by this team, the team here, the people which is here. Hector, well, maybe you don't distinguish Hector. Hector, it was the previous one, and he's there, and he's always welcome to keep helping the operation department. And Raúl Infante, which is here, is not anymore in the department, is in the scientific department, but he's always welcome to help us to execute the observations. And of course, I'm going to focus on JPCAM and the opportunity to observe with the legacy surveys in the future. JPCAM has been introduced. I just put here this as a for completeness in case someone has questions. Well, Right now, we are observing with JPCAM, apart from JPass, we are observing the competitive approved projects that were approved in the last call for proposals. These projects are executed since the semester 25B and is going to continue during the second semester on 26B. 6 projects were approved. The Hercules cluster in JPass filters, led by Stefano Saratini, JAtlas, led by Borja Enviano and Andrés del Pino, Jarras or JArras, to observe asteroids with JPCAM, led by David Moraten, the stellar streams in sextans spheroidal, led by David Martinez Delgado. This project began, but then, due to the maximum exposure time allowed, this project was cancelled. This is one of the reasons why this first period of projects of a shorter, not being legacy service, not giving the time for 5 years is important, is because we knew that we could face some of these issues, like some project needed to be cancelled because technically it was not possible. I'm going to talk about a bit later about the maximum exposure time allowed, but well, this is important. Then the other project approved was Aurora, the time domain in the northern sky, led by Alessandro De Rocchite, and the final project was stellar occultation by Aumea, led by José Luis Ortiz. And this project is the only one which is already finished because it was occultation, and it already happened. I think it was the 4th of May, and it was a successful. It was very successful observation. They observed the occultation, and this project is already finished. The other ones, all of them are begun and are in progress. And we are going to listen in this meeting talks about the four of the projects. Okay. Why we are here is because we are going to release a call for proposals for legacy service with JPCAM. We expect to release this call for proposals for legacy service in next July, so in 1 month. The amount of hours is going to be for all the 5 years. Then total of hours is going to be 1,200 hours, more or less. And these are the hours that will be offered over this 5-year period. This time includes all sky conditions, dark gray and bright, photometric, non-photometric, and also good and poor seeing. Filler programs are always welcome. The observing period will cover the semesters between 27A, the first semester of next year, and until 2031B. All the filters will be offered, 54 narrow band, 2 medium band, and 3 broad band. Unfiltered observations will also be available. Why I put the asterisk is because it has some implications, and you always need technical approval from the observatory. So if you plan to ask for unfiltered observations, it's possible, it's allowed, but because it has implications of the quality of the data, you need a technical approval. So we offer it, but please be aware that you need our technical approval by email. Just send us an email and about what you need for the quality of the data. Like at the end, I will explain later the effects of going unfiltered. The proposal submission deadline will be 15th of September. Of course, this is it can be changed. This is our plan, but so this is our plan. The 15th of September, 2026. We open the time for the international community, and the proposals must be submitted by the PIs via email using the provided document template. It's going to be very similar to the one with the T80. For those of you that were asked for timing with the T80, but anyway, we will release the document when we release the call for proposals, and we always are happy to help if there are some doubts. So, but this time we are not going to use the the web page of the observatory, we will use the document template. The projects will be evaluated, as always, by the time allocation committee of the observatory based on their scientific merit. And the approved programs are expected to start in January 2027. Thank you for all of you that have sent your letter of intent for the project. It has been very useful. I have revised all of them, and I have feedback for all of you. Just the technical part. I'm not. I wouldn't give feedback of the scientific part of the letter. Just the technical part. For those of you that have given details of the technical, of how you want to perform the observation. I have feedback for all of you, so please ask me if I don't give you during your talk, or well, you have feedback for the technical part of your letter of intent. But common things that I have identified. So the maximum exposure time at the beginning, or when we begin the legacy service, is going to be 100 seconds. So please do not enter values larger than that in the exposure time. Later on, while we observe the legacy surveys, maybe we commission the guide sensors, and we will be able to expose with larger exposure times. But at the beginning, we are not able. So please don't put more than 100 seconds in the exposure time. Also, take into account that the maximum time per project is 240 hours per year. But consider the observability also, the observing conditions required for the project. So not all this time is dark or gray or photometry. So be aware of that, and don't ask for all of the time if you want, for example, to observe dark time. I will give some recommendations in the next slide about this. And also one thing is, please use the project total time estimation provided by this tool, the JPCAM exposure time calculator. We will see examples at the last session, but please use this project total time to estimate the required observing time. I guess, I know that in this letter of intent it was not mandatory, but for the proposals will be mandatory. You cannot say, well, I'm going to observe 30 pointings, and because it's 30 seconds plus the download, the readout time. No, don't do it yourself, because then you are going to do it wrong. And the proposal, no, because there are more, don't laugh, I mean, because there are more, it's not only the readout, there are more overheads. In all of the telescopes, there are overheads. So more or less, they are taken into account in this project total time estimation. But if you don't do that, the proposal may be rejected at the first stage of the technical part, and then it's not going to be evaluated by the CAS. It's not to be mean. It's because it's not going to be realistic if you don't use this total time. I understand that in the letters of intent is more free, no? You have more freedom and it's more relaxed. But please, in the call for proposals, do it with this. And this is not an issue, but a common request that a few projects have asked for observations without filter, and these observations are possible, although, as I said before, a technical approval is required. And why? Because the optical quality of the images is affected. So this means that the PSFs are worse, or can be worse, not much, but a little bit. So what we want to identify is if your project requires a very good PSF, and you then also ask for filter observations, is not going to be feasible. And the other thing also is the flat field correction is also affected. And please also, if you want to talk about the effects of observing without filter, you can also ask, I guess, Alessandro De Roclite. He's going to talk about his project, Aurora, that was approved in the last call for proposals, and the observations of these projects were unfiltered. So he's now the expert of unfiltered observations with JPCAM.
We're doomed.
Okay. And I remember you that the proposal will be submitted using the document template provided by us. Okay, recommendations about the maximum time. Consider the observability and observing conditions required for your project on average. About 20 hours per month will be available for this legacy service distributed among all conditions. For example, if your project is observable during a limited period, for example, 3 months, and requests more time than that is realistically available under the specific conditions during that period, this will be taken into account during the evaluation process and may reduce the likelihood of approval. We will put at least the percentages of the dark, gray, and bright time is clearer. So we will put in the call for proposal, we will put it, is 50% dark, 25% is gray, and 25% is bright. So for you to do the calculation. The photometric and non-photometric, we have our own discussions, but we will put it or not. Let's see. But at least the dark, gray, and bright time, we will put the information on the call for proposals. You always can ask me the percentages of the photometric and non-photometric if you want some numbers. Okay, these are the recommendations after reading the letter of intent, but please ask me for the feedback for your projects or for your letter of intent. So let's continue with the filters that we offer. With the filters we offer is the JPass filter system plus G and R. And I guess all of us know this filter system, which is unique in the not other facility no other astronomical facility offers these filters, so they are unique. And the special thing is that the unique thing is these 44 narrowband filters. The filters, for those of you that don't know, the narrowband filters are distributed along the 14 spots that JPCAM has. So we have, for the narrowband filter, we have 4 trays, tray 1 to tray 4, and each of the CCDs see through one different filter for this narrowband filter. So when you observe with JPCAM, at the end you have 14 images pointing towards a different part of the sky, but very close each other, and with a different filter. And then we have three other tray filter, which is the tray 5 to tray 7, which is composed by the same copies of the filters. So tray 5 is composed by the 14 copies of I band. The tray 6 is composed by 14 copies of the same filter of R band, and the tray 7 is composed by 14 filters of J band. And I will say in the next slide how we manage to observe with JPCAM contiguous areas. Observing modes offered and supported. There are different readout modes with JPCAM, but what we offer and support is to observe with binning 2x2 using the narrowband trays. So from tray 1 to tray 4, the binning is 2x2, and this is the pixel size is 0.4 arcseconds per pixel. And with the broadband trays, the supported mode and the offer mode is the no binning, so 1x1. And this means that it has a pixel size of 0.22 or 23 arcseconds per pixel. Also, what we support is 4 dithers made by, and the dither shift is 0.236 degrees. This is the recommended and supported, and this is because it's the one that we use for JPass, and is the one that we are sure that what Hector explained in his talk that we are sure that we can give you proper flux calibration and background removal. Of course, other dithering patterns can be proposed, but then we cannot assure the quality of the processing of the data. Maybe one of the things that we can be more flexible, maybe ask Hector or me, and I will ask Hector, is maybe change this shift, so maybe another value. But this is optimized, and at the end is the better. So or is the best one. Also use the pointings need to be defined using this the GPCAM observing planner, which is in this link. We will see examples at the last session of today. And the minimum exposure time is 0.1 second, but small exposure times less than 10 seconds should be justified because it takes, well, it's less efficient to observe with a small exposure time, so the exposure times less than 10 seconds should be justified. And the maximum exposure time is 100 seconds per dither exposure. If you need more time, just make more exposure. Always, we recommend to always do a multiple of 4 exposures because of the dithering pattern needed. And there is no minimum area. The data product, well, this is already has been explained by Tamara and Hector. Well, the important thing maybe is that if the standard supported mode is used, the flux calibrated precision is less than 1%. And well, what happened if you always can ask for non-standard observations. You can do it. So what is non-standard observation? For example, different dither pattern or different pointings that those recommends the JPCAM observing planner, or different filter distributions or no filter, longer exposure times, and different readout modes than those that is for narrow band is 2x2 binning, and the broadband is 1x1 binning, so no binning. And the unfiltered observations are considered broadband. Okay, so it's although because unfiltered observations are already non-standard, you always can also ask for. I mean, once you are not the standard, you don't care, and you can maybe ask also for different readout modes. In case you ask for a non-standard observation, so these cases, the PI must obtain our approval. And this approval should be included in the technical justification of the proposal. If you don't include that, the proposal may be rejected before going to the scientific committee. But different patterns could be proposed, but this can affect the quality of the data reduction, as Hector already has explained. Well, how we observe with JPCAM. Let's go back to the different filters distribution. So JPCAM has gaps between each CCDs, and the 14 CCDs can either share the same filter for broadband observations or without filter, or use different filters in each of the 14 CCDs for narrow band observations. So there are specific strategies to achieve a contiguous area imaging area. Dithering is essential not only for accurate flux calibration, but also for optimal sky background subtraction. And 2 observational strategies are offered. The broadband strategy, the one to observe with tray 5 to tray 7 using GR and I filters. And so broadband strategy is for the trace that all 14 CCDs share the same filter. And then the other strategy is the narrowband strategy that needed for tray 1, tray 2, tray 3, and tray 4. How we manage to have a contiguous area in the narrowband strategy? So the spatial coverage is achieved by observing contiguous pointings shifting each pointing by the effective size of the CCD in both rate ascension and declination. different CCDs exhibit variant spatial coverage. So each CCD observes one part of the sky different from other CCD, but a common central area spans as more pointings are added. We will see videos just after, well, in a few slides. And the broadband strategy is the contiguous area is achieved differently. So with the broadband strategy, the goal is to first to cover the gaps that has between the CCDs, and then grow in area, just moving first covering the gaps, and then shifting for the next pointing towards moving the whole size of JPCAM. And differing is in both strategies is needed. Okay, let's start for the one main thing that sorry, it's because I don't have, okay. One may think that the broadband strategy is easier to understand because it's just covering gaps and then moving the JPCAM. So what I want is to move this freely. Okay. Okay. I prefer to move. No, well, anyway, you have 4 pointings to cover the gaps, then move towards here, then do 4 pointings to covering the gaps, and then move here to the top, do 4 pointings to cover the gaps, and so on. And then in this way, you can have a contiguous area already observed with 4 different. In fact, you see here there are 16 pointings, but it's because also so each area here. It has 16 pointings, but it has 4 to cover the gaps, but each pointing has 4 pointings for difference. So at the end, in total is 16 pointings here, 16 here. But if you don't count the differing, which is not count, it is not count as a pointing for the estimation of your project. So here you have, for example, you have 24 pointing because it's 1, 2, 3, 4, 5, 6, 6. 6 multiplied by 4 is 24. Each area here is composed by 4 pointings to cover the gaps. Well, what about the narrowband strategy? So let's focus here now in the narrowband. Just see one filter, which is here. For example, here we see this JPass filter, which is close to is H-alpha filter in the res frame H-alpha filter. And well, if you observe, if you shift your pointing by the size of the CCD, you have a contiguous area in that filter, which is now here is H-alpha. So now we have 69, 70, 71 pointings. So you want one more pointing, and contiguous to the shifted by one CCD, and you grow in area with that filter. In this case, the H-alpha. The H-alpha filter. And now we have here, the end is 100 pointings in this example. So with 100 pointings, you have this area observed, which is almost 21 square degrees with H-alpha. But now, what happens with the rest of the filters? So then you have, when you take into account all of the filters, now is H-alpha also plus the other filters. You have these 14 different areas, but at some point they start to see the same contiguous area, which is starting now. Now you start to grow in common area with 45, 46 pointings, which is this area here is what is labeled by common. So now you add more observations and you start to grow in the area in common with the 14 filters until you reach 100, which in this example is the end. So with 100 pointings, you have this area in common with the 14 filters, but you have 14 contiguous area with each of the individual filters. But in total, in this case, is almost 7 square degrees in common with the 14 filters. Of course, you don't need to manage to define the pointings. We have this, the JPCAM Observing Planner, HOP, to plan the pointings to cover a specific rectangular area. At the moment, it can just be rectangular area and also defined in equatorial coordinates, is what is available right now. If you want other things, you have to do it yourself, but also always with help of with support of the observatory, and we can always talk. But right now it's rectangular and in equatorial coordinates. You can define the rectangle using corners, center or corners, or the center plus the length of the box, but also the number of pointings in right hand section and declination, the dimension, which is called the number of pointings and piece. This was available in the previous version, but here, because in survey mode, it's very useful to define not with the number of pointings, but define the area you want, and then the tool gives you the pointings you need to observe in that specific rectangle. Here you can go to the tool and use it. I don't know what I did, but I think I pressed some update the web page. Okay. So if you have doubt, please, there you can read the documentation, which is, you can go there and press the help button, read the documentation. Here I'm going to present just the main points, and we will see a specific example at the end of this, at the end of today. So I think it's at 5 o'clock. So what do you need to define your pointings in the development strategy? So you need a name of your choice that defines your object, your field, your project. You can put whatever. This is arbitrary. It's something that is helpful for you, the field prefix. Then you need the coordinates that, depending on if it's defined using the center or the corners or the piece. So these coordinates mean something different. The area definition mode, you can choose corners, center, or piece. And then, well, again, the corners define, it gives you different options depending on the area definition mode. We will see examples later. The dice, so true or false, please use true. If not, explain me why. And you need the technical approval. But use of dithering is highly recommended, and it is the supported option. And as the shift is the default shift, use it. And if not, also you need technical approval. There is an option to not cover gaps in the program strategy. Remember that internally there are 2 pointings made by default, but then there are people that don't care about the gaps. I know why. I'm not going into the details. But if you don't mind about the gaps, because and you want to observe more area, it's more efficient. But then you have gaps. You can use the no cover gap option, and then it will give you the pointings. But to grow in area more efficient, but you will have gaps within the CCDs. So this is also not well. If you have doubts, just ask me also in this meeting or by email. Just to have an idea of how many area per pointing you have, here it is just for you as a reference. This is recorded. We will try to share the presentations, but here is how much area you have per pointing, in order for you to know how many pointings you need to cover a specific area. For the narrow band, the same. You have for the narrow band, what you need to choose here is in tray. You need to choose from tray 1 to tray 4. Then you will have the tool will give you the pointings for the narrowband strategy by default. The coordinates that fit the rectangle is the same. Then you have the option to choose specific filters. We will see examples this afternoon, because then you may don't care about all of the filters. You just want, for example, three filters, and then you can focus on the common area with just 3 filters if this is your case. And in this case, you don't have the options to not cover gaps because it doesn't apply. We will see examples in the afternoon. One important thing is this, that's the reason I put this, is that you can download the DS9 region of the common area, but also you can download a zip file with all of the regions for each of the individual filters. But well, the most important one, I guess, is the common area. You should download the DS9 region and put it on your field. And this is because at the end, this tool is not perfect. It fails by a very small percentage, you know, like maybe 1% or even less. But it can fail. So if your object is on the border of your rectangle, you can miss it. So please use this. If you care about the borders, download the DS9 region and put it and plot it in your field. We will see examples this afternoon. And in this case, well, if you want to know a very rough approximation of the area you have, depending on the pointing, you can use this straight line. This is an approximation and it's just applied around 20 degrees. So be aware that this is a rough approximation. Don't use this black line, use the blue one. In fact, it's not a straight line, but well, as a first approximation, you can use this if you want to know how much area you will have with 100 pointings, or 400, no? Or so on. It's a very rough approximation of the area in common you will have. This FCC area is the full common coverage area. So this is the common area. Okay, now what is the time I need to reach my desired depth? You have the JPCAM exposure time calculator. Please read the help if you have doubts. There is an important change. Well, here we will present the main points, but please read the documentation. Is well explained because it was written by me. But anyway, if you have doubts, please ask me. I mean, maybe there is something that is not clear. There is an important change from last version, and this was because in the last version it was very confusing. Now, so the most important thing, the most important change is this exposure time. If you remember the exposure time in the last version, or it means the total time, including all the exposure time. Now, this exposure time is for each exposure. So it's what is common in all the exposure time calculators now. So now we are doing what almost all of the exposure time calculators in other facilities have, which is the definition of the exposure time is defined by each exposure. But because we did it differently in the last call, and now I'm reminding you that now there is a change. The exposure time is for each exposure, and the maximum is 100 seconds. So well, here you have all of the inputs that you need. These are common to other exposure time calculators. This is not, I guess, there is nothing very different from other exposure time calculators, but the important thing is please a maximum 100 seconds, but also you can define not the exposure time but the desired signal to noise ratio. So then you have to, we will see examples in this evening, but the desired signal to noise ratio is disabled by default. So this box will be the box of exposure time will be enabled only if desired signal to noise ratio is empty, which is the default. But then the desired signal to noise ratio is going to be available to fill if the exposure time is empty. The number of exposures we support is 4 or multiples of 4 to do the dithering. And remember, this is very important because this is something that I always do wrong. So it's very easy to don't have your estimation correct. So the binning should be 1 if you ask or if you are doing the estimation for I, G, and R or open, and the binning should be 2 if you ask for tray 1 for the narrow band, for tray 1, tray 2, tray 3, and tray 4. Please remember to put the current binning factor because you can have more depth, especially in the narrow bands. If you put 2, the factor 2, you are going to have a deeper observation. So you are going to plan you are going to plan better your project if you use the binning factor correctly. So this is very important, and I'm going to tell a lot of times. I'm going to repeat it because for myself it's also sometimes I forget. Okay. Here I remember again that the maximum exposure time is currently 100 seconds. Don't put more, but this limit may be increased during the execution survey phase when guiding sensors are commissioned. But we don't ask when this happens, or you can ask it, but we don't know. So I think we don't know. Maybe there are people that can give an approximate date. If a project requires deeper observations, just increase the number of exposures. And ideally, multiple of 4 for do the thing. Here I just put an example of the GTC output. We will see later today. Also the GTC project total time. So this is in the same page, but on the bottom of the page. So once you decide the exposure time, the number of exposure and the number of pointings, you can use the GTC project total time to estimate the project total time. The number of pointings you should use in this tool is the one that is shown on the title of the JPCAM observing plan. On the hub, when you define your pointings, then this figure here, it's a number of pointings equals blah. So this number is the one that you have to put here for each of the traits that you want to observe. So here, for example, I have 5 or 500. So I put 500, 500, 500, 500. So if you want to observe the JPass in the JPass mode, although changing a little bit the tray 4. So for example, to do 500 pointings and 60 seconds exposure time, and with 4 exposures, we will need 200 hours in total. It's something doable in 5 years. Okay. And how can I plan a specific observation? There is an example case to observe M101 with the JPass strategy, using the hope and the GTC to obtain the pointings, area covered, exposure times, and total project time. This is in the observatory web page, which is in these links here. So here we have the link to the observing tools, and here is the link which is in this web also. The link. This link is not. I should correct it. Okay, it's not a good link. Now I'm realizing. Yeah. Okay, but if you go here, you see if you go to observing tools, you see the proper link. This link is not a good one. Sorry, I will correct. But anyway, there is an example case, a PDF, a document explaining how to plan the observations with M101, which at the end M101 is here. So and at the end, this documentation gives you the pointings at the total time, the depth, to observe this area in common with all of the narrowband filters and this cyan or blue area to observe with the I-band. Okay, go to the document, read it. We will see other examples where I'm not going to repeat this example, which is already there, and then we will see other examples. And then to finalize, there are more tools, but this is once a project is approved, it is necessary to submit the phase 2 of JPCAM. Where this is for the approved project. So for those of you that have your project approved, you will need to use this JPCAM phase 2. It's already there. You don't to ask for the time. You don't need it. but no, you should know that it already exists. And also there is a JPCam tracking tool. So once a project has started to be observed, the status of the observations can be checked via also the tracking tool. All these tools are always developing and are not the final ones, but here in the tracking tool, what you can see is just the pointings that are already being observed with a specific trace, but it's not linked to the tag data or to the observations itself. So this is the end, but remember that we are going to open the call for legacy surveys with JPCam in July 2026. JPCam with its large field of view combined with the filter system offers unique capabilities. The observations will be carried over 5 years, from 27 to 2031. The total time will be 1,200 hours for these open time legacy projects. The available observing tools to define your project is the pointing planner, HOP, the exposure time calculator, GTC. There is a default ether pattern and a default pointings pattern given by the HOP. Please use them or ask for technical approval. And all of the filters are offered. Also, unfiltered is also an offered option. The details of the call will be published in our observatory webpage. And the expected deadline for submission will be 15th of September. So save some dates for work on this during the summer. And if you have questions on its help, please ask in this email or through me also. You can ask directly to me, but also in this, if you ask in this mail, the question reaches maybe more persons that can help better than me. And thanks. This is all.
The 100 second limit for the exposure time, it's also valid for global filters in full moon.
Yes.
So it will not saturate 100 seconds?
Well, if you observe the full moon, yes, but I think if you don't.
I mean, but due to the background of the sky.
Yeah. Well, we don't observe very close to the moon. In fact, we have observed very close to Mars. Now I don't remember how much time we observe around Mars, but because our limit is to observe 15 degrees far from the moon, with this distance, it does not saturate. It does not saturate. But we don't observe closer.
Sure. Not even in the genome.
We haven't observed maybe with Ivan.
I think
okay.
Saturation may be close.
Okay.
On the second.
Maybe we don't have the Hector is here. I don't see Hector. Sorry. Okay. Sorry.
No. Well, we don't observe with G1 currently, and we observe with I1 for G1, and the observation time is 30 seconds. Actually, is part of the nominal exposure time for the now ones in order to avoid saturation. Of course, if you are observing the larger the time, the more saturation you will have. So that's an important point. The limit of the 100 seconds is because of the tracking and the quality of the image that you will get from that. Saturation is another aspect.
Yeah.
And you mentioned also the question of the background. This may impact the background that you can have on the
compromise.
yes, this is something that in J+ we tend to observe I1. So we can go
With the vision.
No, but we are very far from saturating. We are very far.
Yeah, but I'm looking in this case for
The background.
Maybe.
as a reference.
Adriano has a question.
Yes, hello everybody. Okay, just to make sure, you mentioned that it is not mandatory to have the 4 pointings strategy for each, let's say, field, because somebody may prefer just not to cover the gaps. Is that correct?
That's correct. Yes, yes, yes. And it's more efficient to grow in area. Yes, there is an option to not cover gaps. We can see the example this afternoon to use the tool. But yes, there is here. So there is an option. This is the. Okay. There is an option there. There is no cover gap. So if you tick that box, it will give you the pointings to have a contiguous area with gaps, and it will be larger. We can see examples this afternoon at 5 o'clock. I think it's at 5:15. We can see examples, and if you have doubts, you can always ask me.
Okay, and given that if you go unfiltered, if you go open, the quality of the data is degraded, maybe using 2x2 binning is recommended in that case.
I don't know, maybe. But maybe the problem with unfiltered options is also the flat field correction. We don't observe we don't observe that much flat fields without filters, but well, at the end we haven't observed that much. Maybe in the talk of Alessandro,
I can expand on it later.
Alessandro will expand a bit more later. Because in Aurora we have
I'll press one by
one. Okay. I don't know the effect, but yes, it can be tested, I guess, at least.
Yeah, and last, so I guess that there will be an over demand of dark nights, maybe, or dark times. So how do you usually resolve these kind of things?
Well, it's the proposals are ordered by scientific merit, by the committee, the time allocation committee, and then we observe the ones that are ranked highest scientifically.
Okay. Thanks.
And the committee is public, is in the webpage, in case you want to know who is.
You want to bribe them.
But also it changed with time. It's not always the same. So now you see some of the members, but the ones that are going to evaluate these proposals is not going to be the ones that are now members.
I just want to comment a couple of things. I forgot to mention, this is related with observing without filters, is that one of the advantages of observing without filters is that you don't get this, you get a little bit more area necessity, because given that the buffer is on the filter, you are using no filter, you actually get all the area of the system. This one thing. And the other thing is just a comment we need to explain why we propose some way of observing, in particular for the platforms and the meaning. It's because the amount of time, you agree with me, the amount of time that we have for getting the platforms, that is twilight exposures, is limited. We have a lot of filters, so we have a project with JPass that is running. We need for sure platform for that project. So this limits our room to be open to other configurations that require an extra platform. That's why, in case there is a non-standard, let's call it like that, way to observe, that we need to be this stuff.
sorry, but we cannot really hear anything when you're answering or making questions from the room.
Okay, I will sum up. So what Hector has commented is that the reason to offer these mini modes is because we have the JPass project. We are observing the JPass project, and to correct the JPass project by flat field correction, we need the proper flat fields, and we need to observe them. We need the sky flats to correct properly from this correction. And so what we offer is the readout modes of JPass, because offering different modes, it will imply to observe the sky flats with different readout modes, and this will affect JPass. So this is the reason to observe or to offer these binning modes is just because of the flat field correction of JPass and the limit amount of time to observe sky flats. Okay. So if there are no more questions, let's continue with the next talk, which is going to be the last talk from the observatory. This talk is going to be by Alessandro De Roclita, who's going to be about. He's going to talk about the JPass observing strategy, the hard-won lessons, and 3 tips to help you to define your surveys, your legacy surveys.
So you may wonder, what is this guy talking about, since he doesn't work for the observatory anymore? The thing is, before Javier, there was Hector, and before Hector, there was me. And I had the dubious privilege of coordinating the second phase of the design of the observing strategy of JPass, which happily ended up with me going to a psychiatrist. I think it's important to explain that the last part of this presentation is solely my responsibility. So I haven't shared it with CEFCA nor JPass collaboration, so it's just me talking at the end. All right. As Silvia already commented, JPass was both 8,500 square degrees. At the beginning, the footprint was the poncho and the camiseta, as we call them. The problem is JPCam is not, but doesn't behave well when you have shapes. It behaves better with rectangles, or even better, squares. So the second biggest mistake of my life was to embark in this discussion, which took 2.5 years, 3 years. And the problem is, if you move, some of the fields we wanted to observe were north, some were south, some were east, some were west. It took 3.5, almost 3 years before we got to what you're seeing here. The first year, 1,200 square degrees, second tier, 8,500. As I said, I was in charge of the observation since the beginning of J+. And at the beginning of J+, you can see here, I was optimizing for moon distance and lower mass. And the problem is you start to get a lot of scattered pointings, and some of those scattered pointings are still around. JPCam doesn't like this. JPCam likes, as Javier said, contiguous pointings. That's how the seeds were created. The idea was to have 5 pointings covering the whole 24 hours, so that you would always have at least 2 pointings observing in a given night.
The filters was another funny thing. 15 years ago, the filters were the blue S14, the second blue S14, the third blue S14, the red S14. You can ask Tony about the discussion. The thing is that this was not feasible. At the end, we ended up having the blues, the 4 blue in the center, what is it, 8 red in the around. And then there was some discussion. There was some swap between the central ones of T2 and the central ones of T3. Just to show you how an SED of a star looks like, this is a white dwarf. Use a star because it's easier and because it's more interesting. So this is the SED of a white dwarf, and this is if you only observe, only if you observe in tray 1, only if you observe in tray 2, tray 3, and tray 4. You can see that H alpha falls in tray 2. This is important. And you can see some of the Balmer lines in tray 1, right? So tray 1 and tray 2 carry vast amount of information, especially for stellar astronomers. Sorry, I'm a stellar astronomer in case you didn't know this, and for the both people who don't know me in this room. And the thing is, not all trays are created equal, because not all lines are created equal. So we asked the science working groups, what are the what are the filters you're more interested in? And this was the histogram. And if you accumulate it by tray, you get that tray 1 and tray 2 were the most interesting for the JPass collaboration. Which is the reason why tray 1 and tray 2 were the ones that we all considered priority. Getting there in a moment. The exposure times, they've basically been fixed since forever. 60 seconds. Back in the day, we used 3 sigma limit. Nowadays, we would, if you compare this figure with the paper that Hector is preparing and my paper that I'm preparing, we use 5 sigma limit. So it's a bit more tough to compare, basically, brighter magnitudes. But basically, this is the shape we always expected. We knew it was going to happen. And the goal was to boldly go where no one has gone before. Basically, to go deeper than, for example, Sloan. Back in the day, DESI didn't exist. Speaking about going where no one has gone before, there was the problem of the detection then. God, that was tough. Anyway, the thing is, again, you wanted to be where there was nothing else. So obviously you can't compare with LSST, which is up here. Sorry, you go fainter up. LSST is up here. But LSST, fortunately, is in the other hemisphere. So for our hemisphere, we have to see what to do with broadbands. And the only real comparison was PANSTAS. But we only have space for one tray of broadbands. So what do? We have the option of G, R, and I. At the end, again, after painstaking discussion, we selected I because a deep I would allow us to get also faint blue objects. It wouldn't work the other way around. Deep G getting very red objects. All of this ended up into being the survey speed, which Carlos Hernandez Monteagudo and I evaluated independently. There were diverging interests, to put it mildly. So since trace 1 and 2 had more interest, the idea was to have 800 square degrees per year in trace 1 and 2. 200 square degrees in the 4 narrowband filters, narrowband filter trays. And the idea was to use the first tier as using the whole four trays as a proxy to see if we understood the system, blah, blah, blah. As Jordi Sepa used to tell me when I was at the ISC, la realidad termina siempre imponiéndose, and you may have noticed that there was an issue in July where one seed was falling and the other one was rising. And what are the odds you start observing in July? Yeah, apparently 100%. So this is why Hector decided to invent the JPSV seed, which is the place where we started observing. And again, realidad termina imponiéndose. We started observing with this sequence, basically observing in squares, in blocks, and you basically grow these squares. We go much slower than we expected. There is a series of reasons for this. Some overheads that we didn't understand beforehand, and also the fact that JPCam has a lot of inertia and needs a little bit to start. So my last 5 minutes is the part where I take full responsibility for what I'm going to say. So my way of thinking about JPass is to think about 56 independent surveys, and then you stack them together. It's sort of what Javier was commenting. Until I started with this project, I was a big fan of Panzer diplomacy, which means this is how it's going to happen. End of story. And it had worked so far, but it didn't work in this case. The discussion about an observing strategy for everyone who's dealt with observation is never linear. It's actually quite circular. You go like, I want to do this, you can't. So basically, it's always a balance between what you can and what you want to do. And the problem, especially with JPass, was always a short blanket. So at the end, the beauty of this is everybody ended up unsatisfied, yet everybody went away with at least one win. There's only one science working group that I know of that didn't win anything. Now, tips. So this is the number of stars number of objects fainted at magnitude 20 in Gaia in the sky north of declination 20, minus 20. And you can see that there is 1/3 of the objects are within 5 degrees from the galactic plane. So personally, as an astronomer, I would feel offended if no one would go observe there. But that is basically where everything is. 1/3 of the objects in the sky are there. So if you miss it, it means we're not doing our job properly. Thankfully, Marcelo and Jairo are actually doing things right. And then there's a few baits that we left. The decision was literally taken in this room, around that corner. And we left out, these are the regions of sky with the highest amount of refereed papers. So you can see there are some regions of sky which are intrinsically more discussed. So, and I am assuming higher number of papers, higher discussion, more interest. And we left on purpose out the North Ecliptic Pole. Jean Tao is going to speak about this. The Kepler field, Yang Wang is going to speak about this. Virgo, Luis is going to speak about this. Correct. And M31, Andres and Borja are going to speak about this. So it looks like our strategy worked. So we left the baits out for them. Last slide as well. So instrumentation golden rule. A telescope and an instrument are only as good as the science they're taught for. You can go to observe quasars with HARPS. You're going to waste time. You can try to observe a kilonova with JPCam, you're going to waste time. Go to Grand Tecan, don't come here, right? Advantages of piggybacking on JPass. You already know the performance. You can just go to the archive. Tamara showed you how to do it. You already know what you're going to get. Just another SkyAga. You have guaranteed calibrations, as Hector and Javier were mentioning right now. We do flat field for JPass. SEFCA will always maximize the efforts in data reduction and calibration for JPass, just because it's where we have more data. It keeps getting in. It's not because one project is better than another. Actually, it is, but yeah. Now, what are the advantages of changing the filter distributions or observing with or changing the trace in the thing, in the layer? None. If you're smart, just piggyback on JPass, just observe out of the footprint, and you're going to get the best data that we can provide. Otherwise, just wait for me to talk to you about Aurora and see what pain actually means. And thank you very much.
Sorry, just to, of course, Alessandro has said that it's not official. And I will say that unfiltered observations, of course, you are right, and you will explain much better than me what are the consequences. But I push the people to ask for the air band and the G band trace. Sorry, right? Well, yes, everyone is listening. I mean, they are in principle, they are available if you want to use them. I don't agree with Alessandro. It's true that we haven't used them that much, but it should work. But of course, the unfiltered observations, well, that's another story. Question. Online. So if not, now we have finished our presentations, the ones from TEFCA, OAJ, JPass, and we move now to the scientific contributions of the projects that have been sent the interest to be presented in this meeting. So now, how much time I said?
You said 15 minutes.
Plus 10.
Plus 10?
Okay. So it's 15 minutes each of you, plus 10 of the questions. We can be flexible more or less because 10 minutes is plenty of time. So, and we are on time? Well, less.
No, less.
Okay. 3 minutes. So we start with an AI-assisted unfiltered time domain survey with Kabbalah Survey Telescope, given by Alessandro.
Long time no see. All right. So I'm giving this presentation on behalf of most of the JVAR team. And this is part of the studying interest in non-classified objects, SYNCO project. So you can split this project in with 5 resources. Gaia, I hope I don't have to introduce Gaia to anyone. J+, that we already heard about. JPass, if I need to explain what JPass is, probably you shouldn't be here. JVAR, which is a time-resolved broad and narrowband automatic survey done with the TAT. And I'm going to share my pen. So a little bit of timeline. Already in the 1920s, some of perhaps the second most important discovery of the 20th century was done with a wide field camera, right? The limit calibration for the C-frame. Took us more than half a century before we started to use more than one filter, always ground-based, ground-based and one site only. We moved to space in the 2000s, Kepler TESS cohort. And then again, in the 2000s, we also started ground-based server sites, so IPDF, Assassin, Atlas. And as far as I know, JBAR is the only one that uses narrowband filters in time domain. And there's another funny timeline. In 2021, we were coming out from the pandemic, and the JBAR core team, we were starting to discuss what do we do with, are we going to do something with T250? And Hector said, why don't we go white filter, no filter whatsoever? And since Hector and I, we have this tradition, we always disagree in public, I was like, rubbish. Then in February 2025, there was the call for proposals. And on the 9th of April, during a work in progress meeting here at CEFCA, Javier, who left, went and said, oh, we tried to do some unfiltered observations. It works. And I went like, the hell, let's try it. So the core idea was, let's observe in white light, 11 epochs. This is literally JBAR. 60 seconds per image, 40 third observations, 3 fields only, so that we cover the whole thing, the 24 hours. So we can observe anytime, right? We made one small mistake that I'm going to comment in a moment. Since it was an interesting time because it was right after the first reasoning model, ChatGPT-03, came out. And ChatGPT was already offering deep research mode. So I said, you know what? Off you go. Give me a name, analyze the scientific topic, and find me 3 pointings. Had I looked for the pointings myself, I would have ended up in a loop with myself for the following week. Did it in 20 minutes, and he gave me 3 fields. 2 are famous, Northern Hemisphere, Lockman and the North Ecliptic Pole, and one is right in the Milky Way. And I was like, are you mad? And I was like, that is actually cool. You know what? Worst case scenario, the data are going to be a disaster. And since I was there, I was like, I read the thing that it has produced. And I was like, will it be able to write a scientific rationale? So I was like, I decided, okay, let's make it right. The scientific rationale and the technical justification. Scientific rationale was okay. Technical justification. Mind you, I'm saying can, I'm not saying should. This was happening in April last year. In September last year, there was this series of AI recommendations from the Space Telescope Science Institute. I only summarized the questions. Would I stake my professional reputation on this, on the output you get from the LLM? Do I have the expertise to critically evaluate this output? And does it give the appropriate level of, does it give me the appropriate level of ownership? Now, I know that there are some people who still use LLMs as 3 years ago. You just ask a question and you use it as a glorified tool, which is fine. just basically not using an LLM, but it's fun. So if you manage to start an interaction, it turns out that you can actually get interesting stuff out. And there's another relevant question. What is it that matters? What is it that is evaluated when in a time allocation committee? Is it the author or the authors? Is it the idea? Is it the text? Is it the strategy? In other words, how important it is that I give my ideas, my logic, my expertise to the LLM, and the LLM writes the text on my behalf. So anyway, as an experiment, I said, let me try to let it write as much as it can, fix what it doesn't fix, get approval from my co-authors, send it, and let's see what happens. Woohoo! It got approved. Mind you, this is 1 year ago. Now, these things, they write even much better. They write much better. Plus, it was ChatGPT. Claude wrote much better back then. There's a beautiful sentence. Every LLM that you have now is the worst that you're going to have tomorrow. So yeah, that was interesting. It was an interesting exercise, but the best exercise was still to come, because I have a data avalanche coming. So one exposure of JPCam is one exposure of one CCD is 100 megabytes, zipped, not zipped, compressed. This means that one field is about 210 gigabytes. This means that since I have 3 fields, the amount of data I'm dealing with is the JPass EDR. And I don't have 400 people as JPass. And I don't have the UPAD working for me almost exclusively. So I was like, how do I do this? Oh, right. And this was the first image I got. For everyone who doesn't know, once you're observing white light, you get everything which is bad from the blue and everything which is bad from the red, you get it together. So you get basically the PSF of the blue, so the worst. You get the fringing, you get the coding on the CCD. Everything which can go bad, it does. So this is the first image I got, and I was like, oh dear God. So I had to prepare my own beautiful detected source manager. And there are people who like pain. No, I don't necessarily like pain. So anyway, I asked Claude Code using Sonnet 4.6. So this again is not the best model. I could have used Opus, but we decided to stick to Sonnet to have more space. And this takes care of image retrieval, photometry, calibration, image combination. Prepared the scripts to do all this. Run them in the Safka HPC so I can, I run this in my computer. I take the scripts, I move them to the HPC so that the HPC is never in danger. And then in the HPC, I do everything. Then again, we also have the human manager. And this is Hector sending me a message yesterday afternoon. This is cool. So this is what the BDSM produced for me last night. And this is the quality of the data across the observations. So you can see that sometimes the background goes a little. The moon illumination is very high, and it's when the sky background goes very high. I love it when Javier says, "We had full moon last night. We observed your program." That's like, and I go like, all right, it's a filler. Not like you're supposed to humiliate me like this. This is only for one CCD, right? And the limited magnitude of one CCD, 60-second exposure, is 21.5. Now, there's one thing that we forgot to take into account, and this is a filler program. No exposure time calculator will ever tell you, oh, this is what happens when the weather is bad. So, trick, if you want to do these kind of things, which is what we did with JVAR, and it worked perfectly, and had we applied it here, it would have worked. Just take drive time, put a very generous air mass in the exposure time calculator, remove 1.5 magnitudes, and that is what you're going to get. You do this exercise, you get exactly 21.5. Yes, it was a little bit of a disappointment. Yeah, shit happens. You learn. This was a shared risk, right? It's the logic of shared risk. The interesting thing is, you can get highly interesting non-classified objects, and you can compare with already classified objects. So in this case, you have this one. They are non-unrelated, and the phase coverage is not complete, but you can, in this one, you can see perfectly that it's going down. This one, I was checking it, is actually it's an eclipsing banner. So, long story short, the program actually works. It's not as deep as I was hoping, but the program actually works. Now, the real problem.
What are you trying to do with that? What is the science behind?
The science behind it, I'm basically trying to get variable stars deeper than anything you can do in the northern hemisphere.
For what?
Binary evolution, distances for what's called dwarf galaxies, but not in these specific fields, right? And what I actually care for is any weird stuff. I mean, anybody can look for an outlier, but once you have 1 million variable stars, you get the interesting stuff, right?
Okay.
I know you're new you're new at this game.
Let's try to understand what you're doing. That's all.
So the idea would have been to try to have thousands of square degrees. The point is you have to start somewhere, right? And the thing is, you have, so this is one image, but in fact, at any observation you get 14, and then at any observation you actually get where's Javier? You get the 4d plus 4 different pointings. So this one here is something like 16 square degrees. So lessons learned. So an AI writes better than most people in this room, if not all people in this room. You want to use agents, especially now. You want to use tools and connectors. If you are still living in the universe of it will invent references, it means that you never used an MCP. You use this MCP, which has been written by my wife. And it works because it's been written by my wife and because I've been using it. And there is no shame in asking for help, especially if you're asking for a collaborator who has the whole knowledge of the humanity, infinite patience, does not judge. You can ask this collaborator at 2 in the morning when you're having the beautiful idea. Observing in white light is not for the faint of heart. Learn how to do the tricks with the ETC. The ETC will not help you, so you have to be clever. or rather use my tips. You're going to, as soon as you start observing with JPCam, you're going to be invested by data. And so automatize as much as you can, as well as you can, and interact as much as you can with the dot and with the dpad. And with this, I thank you very much.
Questions?
How many images you have there? Night observation.
Dear God. Thanks for the question. Per night observation, I specifically asked not to observe more than one OB per night. One OB means the 14 exposures of one field, 4 times 4. So 14 times 4 times 4. So at some point, I got asked, more than once, I was asked, listen, this is the only fielder program we have. Can we just stay on it the whole night? No! It would have been just unbearable. I mean, with one night of observation, I would have data for the rest of my life.
I mean, I didn't say it's a bit because there's one half field, it's around 500-600 gigabytes. I used exactly just one hard drive for
yeah, for the people online who may not be hearing, David Morata is commenting that in his project he has 500-600 gigabytes of data. Because it's, yeah, this thing is just a lot.
You have data.
Don't scare people. Questions? Well, I have a question. Do you have a plan to keep asking for more time with Aurora? Okay.
Just for my topic, can you put the images, the one that is corrected from 5?
What? Sorry?
The one that is already corrected from 5. This is just to show you that Aurora is like an example, or let's say it's our best example currently of non-filtered observations, and we can say that that is what so we can see from this image, which is
I piggyback on Hector's comment. Again, for the people online who may not be here in active, he's commenting that Aurora is an extreme case of flat fielding. Because it's white light, right? So I wanted to add 2 things. First of all, I want to thank all the effort of the observatory and the DPAD for everything that I put into this. I'm looking forward to have the API connection to get the data from that data soon. That would be lovely. There was one thing. Oh, right. If there's one thing that I've been working with T250 for more than 10 years now. If there is one thing I'm proud of, it's actually the observation you're looking at. Because this is the plane of the Milky Way. And I can show you, because this I can get on the, I looked at the data. You can do aperture photometry. So this is important because there are people who want to do correctly JPass in the plane of the Milky Way. So if there is one thing I'm proud of having been
doing with T250 is this observation. And thanks.
If I can add something again. The next speaker is going to be Alberto Castro Tirado, and he's going to talk about his project, a legacy survey, or his proposed project, a legacy survey of fast optical transients with the Hubble telescope at JPL.
Okay, good morning, everybody. For me, it's the first time I'm here. So it's a pleasure to come to Teruel and see how TEFCA is going up so quickly and producing impressive results, and to hear from Antonio about the new telescope that I think it will be also make a big change to the science we can get. So here we present you the conception of the project that both Maria Gritsevich and myself have submitted in Selector of Intent. And the outline of the talk is why we are using Wi-Fi service to detect fast optical transients, what fast optical transients are considered to be, and then I will discuss about the project itself. So I start with the Wi-Fi service, and then I will start with the survey we ourselves are conducting since a couple of years, using one of the white instruments in the VOTES network. The VOTES network, some of you, I think you know, was started to be deployed in 1998 with the first robotic telescope in Spain, in INTA, in Huelva, and the last one was deployed in Chile, in San Pedro de Atacama Observatory. And this network was announced in 2022 to be the first network deployed by any country in all continents. So I think we also are proud that Spain could achieve this goal at that time, after 25 years of working together with a marvelous team. Together with me. So just to comment on one particular station, the first one where we installed a robotic telescope is hypothesis number 1. And in 2022, we installed a wide field astrograph, 28 centimeters, providing a 5 by 5 degree field of view. And we have been using this in order to conduct a survey of the night sky every night down to 17.5 magnitude. It's very interesting to conduct the surveys because, as Alessandro pointed out, you may find some wave sources or no sources that you may have detected before discovery, such as Nova Cassiopeia 2021, or you may also see a variable star SW UMA, which we managed also to get some spectroscopy, or even some objects that in the catalogs are supposed not to bright too much, and then you found that they are 2 magnitudes brighter than ever. So I think this kind of science is there when you are trying to do this survey and trying to pick up the variable things that are in the sky. Of course, other teams in other larger facilities can do much better than us when conducting a survey. People conducting surveys for supernova searches or for near-Earth objects that could make damage to the Earth, so to speak, like Atlas in the ground, or TESS in the space, Zwicky Transient Factory, or RASA. I think they also provide valuable information about these transient sources. And I will just focus on the Zwicky Transient Factory because I think it's very interesting how this instrument is working. This is installed at the Palomar Observatory, as you may know, and this is just an image, this is just 1 divided by 64 of the real image. So you can see the quality of the image. Detail about how they are producing this. So this Zwicky Transient Factory conducts survey down to 24.5 magnitude, and the night sky is being observed every 2 nights only, in both G and R months. So it covers 5,000 square degrees per night with multiple images. And this is very important, the fact that it can take multiple images. And they already developed this automatic subtraction software, so they can pinpoint objects that are changing by 5 sigma during a given night. Okay, and the typical time from closure of the shutter to the alert, so the whole processing time is only 8 minutes. So in 8 minutes, they can know there is something new on an image. So this is the mosaic they have, which is 40 centimeters and 16 CCDs. And they are able, as a comment, to detect in 8 minutes whether they have anything new, and then confirm the redshift of the source just going to the larger facilities they have, or even triggering spaceborne instrumentation, such as Swift in the past. So what they are discovering this way, they are discovering the so-called fast optical transits, particularly the so-called luminous bright fast optical transits. So this is how they discovered the first one of this type, which happened to be called the COM, but just because in the Astronomer Telegram tool that provides you with the letters following the year of the discovery, happened to be COW. So this is just for the night of 14 September 2018. So with the software, they came up just monitoring about half of the sky, up to 20.5 magnitude. They came up with more than 260,000. After the first checking, they were reduced to 217,000 sources, and further checking reduced the number to 96,000 real alerts. And about out of these 96,000, 43,000 had 2 images, and they could see the object within 30 minutes separation. So it was real. It was real. Out of these 43,000 sources, when they were, the ones in the close gravity plane were excluded, they came out with just 1,300. And out of these 1,300, only one of those was called fast. It turns out the rise time, as you will see in a moment, was really fast. So this was really very puzzling, because till then no such a fast rise optical object was discovered, and the results were published in Nature. You can see how the media discuss about this. So they made use of the COW in the name of their astronomer telegram. So they say, holy cow, astronomers got a mysterious new supernova, and also new scientists are giving force. Imagine how this got attention. So this is basically a plot just showing the rise time on here. And then with respect to the peak luminosity, you are able to determine the redshift. So clearly this object, astronomical transient 2018 COW, really was an outlier when you compare with other more or less normal transients, such as supernova, more flavors and so on. So what is clear in this plot I show you is that if your object is on this side of the diagram, cannot be powered by radioactive decay, and on the other side you have this the transients, and basically type 2 and type 2 supernova, and type 1 on there, but they can be powered by radioactive. So what was powering this source? Well, I will not detail too much about this, but basically after detecting this object at all wavelengths, from not only the optical but also from radio to X-ray for several weeks, they came up that what we have in this particular case was also the the result of a massive star explosion, an outflow that you can see here, which could be powered either by a neutron star or black hole, was not clear at the time. So you can compare this with the long duration GRBs, which we know now quite well what they are, which are the collapse of a massive star, and then you have the birth of a new black hole in the universe in most of cases. But here, this is slightly different. You have just ejection of 10 to the minus 3 solar masses, just in 1,000 per unit, and you have also the torus of about 1/10 of solar mass, just very close to the progenitor. So this was really a wave object. The speed was subrelativistic, not relativistic as in the case of GRBs. But it was the first such object, 2018, I remind you. After this one, another 8 or even 10 are proposed now to take place. The last one yesterday was the last one yesterday. So they are really blue. They are very fast. And here you have the light curves in the optical when compared to the brightest optical afterglows of GRBs, such as the GRB of 2013 to this 7 April. So you can see that the colored ones are these fast optical transit. So you can see that, yes, after explosion, I mean, they rise quickly and then they stay there. And you can detect the emission in the optical, and also in X-rays, also in radio, especially in radio is long lasting for even months. Okay, so this is a sort of event that the 3D Transient Factory is able to discover, right? But has to do this sort of high cadence monitoring. And all of them are happen to be close to us. You think that 0.3 is close to us. Okay, so it's important to also perform spectroscopy observations in order to determine the redshift and to see if you get some typical features of collapse supernova. And this is what they are also doing here in a follow-up program. They have mainly ArcTech. So what about the host galaxies? Host galaxies, for these 8 events that I mentioned already, they just start forming dwarfs, spirals, and the offset with respect to the galaxy center is found to be of the order of either 0, coincident with the nuclei, or 14 kilopascal. All right. So this is one of the also interesting ones, and I think this is a very peculiar one because I mean, following this animal naming, it was called Tasmanian devil, but of course this TCD more or less is resembles something. So you get from the automatic naming server, you get the 3 letters, and then you have to think which animal can correspond to TST, a Tasmanian devil. So this was what unique. Why it was unique? Because it was observed to be flaring. So here you have the galaxy, and you have the point source, and you see that in just 3 minutes consecutive exposure. So you have there 15 minutes. You got, I think, nothing here, one flare, same flare here, and then it became dim. So it had a flaring during 5-6 minutes. So this is also very puzzling. This is the light curve of the flare. So you have here, I mean, flaring by a factor of 4 times, just on a time scale of really few minutes only. These are minutes. So this is 20 minutes. You have flare in 20 minutes. So this is quite unusual as well. Already 0.25. So far, this object has been recorded 14 flares. And the duration of the flares is between 10 minutes to an hour, nearly a half, with a duty cycle of about 1 to 10%. So if you observe a field for some time and you have this object, then, I mean, in 1 out of 10 images, you may have one such flare. Okay? So that's it. I continue. Okay? So regardless of the exact origin of this flare, the strongly flaring supports we are dealing with a small emitting region. But the central object is without compact object. We don't know yet whether it's a neutron star, whether it's a black hole, or it could be even this flare due to the tidal disruption of a nearby star from this event. So here you have some examples. And I, of course, don't want to miss the chance to tell you about this particular object, for which we published a letter in Nature several years ago. It was also a flaring source discovered many years before this luminous fast black object. This source happened to be in our galaxy, so that's also interesting what we have to do to our galaxy. We don't know yet what it is. It was flaring. It was detected in X-rays first. So we followed that in the optical, and it was flaring during 3 consecutive nights with flares, as you see here, not in minutes, but on seconds time scale. And we tried to get a spectroscopy, couldn't, because when the weather became clear at Calcasieu, when we have time at the 6-meter telescope in Tellenchuk, just the flaring stopped, and we could do nothing. We don't know yet what it is. I mean, I observe this target from GTC, this once a year. I mean, last year I saw it is about 22 magnitude only in Z band, so it's very rare. We propose in the Nature paper that could be a magnetar, a giant magnetar, but this is just a guess because I mean we don't have any spin period, nothing. We just are waiting the source will become active again to try to conduct much deeper and hopefully successful spectroscopic observation. So all this motivated my team to send this letter of intent in order to propose what we call OAJ, which is a legacy survey of fast optical transit with the 2.5-meter telescope. So of course we make use of this great capability of the 2.5-meter telescope with this large field of view and the possibility of using the broadband filters. So the survey goals are just to detect these fast transients, which could be the ones I just showed, or could be then orphan astronauts in gamma reverse, namely gamma reverse, which in the jet is pointing far away from us, but we see the cocoon emission, the astral emission, and we can distinguish clearly from luminous fast transients as well. And even if we get the cadence we intend to, we can also record flaring if we are happy to point to the right position. So the observing strategy, as I mentioned, is a multi-flight cadence approach in which we observe the field as often as possible. And with the available amount of time, we believe that we can go to 200 square degrees in the 5 years of the project. And as I said, we need to do intra-night visits every now and then over the 70 fields when we have possibility. The strategy will be to use the G and I band filter in order to get also information on the color, which we expect to be quite blue in many cases. I think unfiltered you can get deeper, but as Sandro pointed out, it's always tricky. But I was glad to see that Aurora can produce nice results. Exposure time, we know that they have to be not larger than 100 seconds, probably we have to go to 30 seconds in order to optimize the conditions of the moon, depending on the phase. I'm not sure whether we will like to do that for tethering, because in principle we don't care too much about the gaps between the CCD. According to the time calculator, is 22 to 22.5. But I mean, if we see 1 magnitude less, it's also okay for us, I would say, depending on the conditions. For this 1,200 hours, which we learned that would mean 220, 240 per year. I think we can cover this 200, but we have to do numbers carefully. Now, when I heard the presentation, previous presentations, I mean, it can also work without reaching 200. What I think is very important for us is the synergy with the Bottles network I mentioned before, because the Bottles network means that we have 7 telescopes or 6 telescopes, 60 centimeters, which we can reach 20, 21 magnitude, depending on the observatory, and they are willing to be to respond to any incoming alert. So I think this will be important for following up all candidates we may produce without any time limitations, and we can get color information from U-band to the Y-band if they are bright enough. So I think this is very important, and I think this also will enrich the project, the synergy with our network in more content. So this rapid follow-up, I think, also is most essential, because if we can determine with the color information we can get also with the Bottles network and the variability that is an interesting object, then we can also trigger a larger diameter facilities we have access to, at 1.5 meters in Sierra Nevada, 2.2 meters in Colorado, and eventually the 10.4 meter in Canary Island, La Palma. So from an implementation perspective, we believe the program is low risk in the sense that it relies on established observing mode here in the observatory. And the calibrations, I think they are also clear according to what I saw this morning. So that's the reason why we don't want to deviate too much. It would be here, it's working perfectly, and regarding calibrations, is perfectly not. And what is important is that my team, Maria Messer here, and also the rest of the team we have in Granada, they have long-standing expertise in detecting transit for, 2 decades or even more. And now we have learned a lot when doing our own survey with this 28 centimeter telescope, and then just checking everything we have on the 5x5 degree image, whether there is unusual bright compared to catalog, whether it's something new, or whether it's there because it's variable, but it's not interesting at all. I think we also have reached this point to pinpoint what is important or not. And also, given the amount of data we will get, if we proposal we granted, for sure we need to implement AI capabilities, as I mentioned. And I think we are also doing this in our own survey, in which we are integrating the convolutional neural networks or vision transformer for classifying the events we may have. An optimally trained CNN will be able also to distinguish whether we have something really weird, let's say something that is not worth to look at. So to conclude, I would say that fast optical transients are a rapidly evolving field in time domain astronomy. And they encompass different types of objects ranging from, I show first, this luminous bright fast optical transient, LFEOT, or flare stars in our galaxy, or even orphan astrolog in other galaxies. So the project we propose, JFast, is really focusing in order to get this 200 square degree monitor and try to pick up any variable things there. We will follow up with the Bottles network right away and trigger large diameter telescope to pinpoint at least the redshift or even the nature according to the specificity of the object we may consider they are more interesting. And finally, just I mentioned that this Bottles network will be working together with this survey in order to help classify the events and trigger large diameter. And I think that's all. You need more info about our network, then you can go here.
Thank you. I have questions, but I prefer to let the people ask. Okay.
Thanks for your talk. Is there any particular filter set you are not interested in?
I think in principle we'll go for Y band, and I think G and I to get the color information. I think at least it will be there before G and I. We have to prioritize over all. Unfiltered, I think it's very interesting also because you go deeper, but I think it's also tricky. So in principle, I think we will stick to G and I.
Two questions which are somehow related to each other. To have the G and I at the same, because I understand you want them at the same time on the telescope.
Well, at the same time, I think not possible.
No. You want them in the same night.
Yeah.
Right. So, how are these 200 square degrees distributed in the sky? Is it one patch of 200 square degrees, or is it several patches?
No, I think they will be very close. I mean, we will not jump. So we will focus on a position. We will stay there going around. But we will not jump from one position to the other.
So it's a seasonal project, basically.
Yes.
Very interesting. One of the general handicaps that the large surveys have is the cadence of communication, because many times they just appear at the end of 5 years. I assume that for your project this will not be the case. Sure. Do you have an estimation of typical, I don't know, how many publications do you expect to produce with this?
I think we will not need to wait until the end of the project to publish, let's say, a statistical paper, but I believe that we will be able to find some interesting events to follow up. So, I mean, minimum publication this year, I would say. Probably not, but probably not. What? Well, yeah, I mean, with the survey we are conducting, I mean, we have many interesting sources, but we are covering the sky 1-2 nights. So then, if there is, like we have seen, a place that was found to be too magnified than the catalog, and I think we even issued an astronomical telegram. So, well, again, if we found something interesting, of course, we have to issue an alert. So the people who observe it, it's really interesting what we found. In this will not matter at all. But we publish an alert, and we work on the publication, getting more observations, of course.
Is very modest. By now, it has like 17 nature papers, maybe 8 science. In addition to the so I think the outcome will be very
Yeah, I mean, if we find interesting objects like the one that Alexander was mentioning, I think these are unique objects, and you can score to high impact factor.
I think we have to. I want to talk with you, but are you going to stay here and also tomorrow?
Yeah.
Okay, because we need to talk about the technical.
Sure, I imagine.
Okay.
I imagine.
So next, well, let's start. Okay. And so the final talk before lunch is David Morate's talk. He's going to talk about photo-arrays, near ultraviolet spectrophotometry of solar system small bodies with JPCAM.
Morning, everyone. It's a pleasure to be here again. Months away. Today, I'm going to tell you about what we have done with JPCAM in regarding asteroids. Okay. Years ago, when I was starting working with JPLAS, I saw this nice filter system
and also the survey strategy. And of course, it was useful for our field of studies. But then, when I heard about JPass, and I saw that huge filter system, I was thinking, man, this would be much better for them. But when I knew about the survey strategy, I was thinking, okay, maybe not so much. But since then, I was thinking, there has to be a way to take advantage of this instrument and this huge field of view in this telescope. So with that in mind, last year, talking with some of my collaborators, we developed a pilot program to check what could be done with this. So I'm going to briefly talk about some asteroid science in the beginning, just to introduce you, because as far as I know, there's only one solar system here. So, okay, thank you. We're not alone. So, for those of you that know, asteroids are flying rocks, objects that orbit around the sun, have no atmosphere, irregular shapes, and sizes from a few meters to hundreds of kilometers. And the scientific motivations behind their study is that they offer a lot of information about the origins of the solar system. Some of them have organic compounds in their surfaces, maybe even water in some different states. And of course, they're also important in the sense of space missions and for planetary effects. These objects are located in the majority of them in the solar system are located in between the orbits of Mars and Jupiter. Of course, there are many more outside the orbits of June, and in between Mars and the Sun, Earth asteroids. And the main way to study their surface composition is to study the light that they reflect from the sun. As I said, these are rocks. They do not emit light by themselves, or at least not in the visible range. And then we observe, we recover the light that they reflect from the sun here. There has been a lot of works regarding taxonomic studies in the past, mainly in the visible. There are also studies in the near infrared that relate these objects to different compositions. Maybe the ones that we call primitive, that are related to carbonaceous materials, the ones that we call rocky, that are brighter and related to silicaceous materials, the statites, basaltics. There are a lot of compositions if we try to find their meteoritic amounts. But there's a gap in knowledge in the near ultraviolet that could offer information that is very hard to obtain from the Earth due to the huge atmospheric absorptions that we have in the field microregion, which is the one that offers more information regarding the organic materials, water, and so on. This region is highly correlated with some type of structures in the near ultraviolet regions of asteroids. With this in mind, and knowing what has been done in the past, well, here I show you the filter system of JPass, JPass and JVAR. We have a good number of filters in between 0.3 and 0.5, but in any case, these are just 5, 6, if we count the G1. In Gaia, they are using how to say that? Highly refined spectra. Having more or less high resolution spectra, they are offering just, I think it's like 3 or 4 points below 0.5 microns. Of course, if we look at the LSST, we only have 2 filters below 0.5 microns. But we look at the filter system, JPass, JPCAM instrument. we have around 12 to 16 filters in this region. And one of the first taxonomies of asteroids that was developed like 40 years ago used, I remember what it was, the 8-color asteroid survey. 8 filters scattered from 0.4 more or less up to 0.9 microns. 8 filters. We have more than that in the near ultraviolet region with TPCAM. So I thought, why not? Let's try to go for this. This is what the spectra of an asteroid, the complete set of filters observed in JPCAM should look like. But as we will see after this, it's not as nice as it should be. The observational strategy that we thought about was mainly focusing on regions where the density of asteroids high enough to be efficient when looking at some region of the sky. So of course, we have to go to it. With this in mind, we selected several fields observable from the OAJ and with high enough altitude during a long enough time, because when looking at the exposure time calculator, more or less the things that we thought that we would be recovering using these exposure times were acceptable for us. It was around, as I will say after this, the initial expectations were around 50, 60 objects in the near ultraviolet region field, and much more, around 200 or so, if we took into account the whole wavelength range. So, with this in mind, we use the typical dithering that has been said once and once again, again and again, 4 times, and with 30 seconds of exposure. With a mosaic of 6 times 6, which equals in total around, well, I don't know, 36 points. In total, more or less 1.5 hours per frame. But as I was saying before, since the near ultraviolet is the near ultraviolet filters are scattered along the 4 trays, we need to observe it. But if we don't have our fields high enough in the sky during the time that we need to observe them, how do we do things? This is the less worse approach, could be said. 2 trays in one night, and in a consecutive night, another 2 trays. It's not optimal, but it offers enough useful information, and you can recover the same objects that were in this field in the previous night. You can recover them in the second night with a different set of filters. Total time per night, more or less, was around 4.5 hours. As I said, we looked for fields that were above given elevation during at least 4.5 hours. The minimum useful data for us tonight, and as I was saying before, we would get around 8,000 images per observed field. Problems, caveats. The continued optimal time or optimal observing conditions are not easy to achieve. We asked for a great time with sync below 1.5. Of course, this has to be maintained during 4 or 5 hours a night, and it has to be repeated on the next one. The observational windows are half a year because you look at the sky during May to September, you will see the ecliptic above certain directions. With that in mind, we managed to observe just 1.5 fields out of the 3 that we asked in Brixton. In any case, there's data. I think it's going to be useful. It has to be curated a lot, but it will be useful. The data, the process to recover the data was using the same pipeline that we have used for the recovery of data in J+ and JVAR. However, it had to be split in 3 different groups of images because otherwise the pipeline was not accepting that many data. As I was saying before, the initial expectations were around 50 objects per field with nice near ultraviolet coverage and 200 for the rest of the range. But reality is not as nice as one can plan beforehand. Here, this is ordered by wavelength recent wavelength, and the first ultraviolet filters have very few observations. Of course, one can expect that around the GR and I regions, you will get many more detections. But since we use the same exposure time for the 4 trains, there's going to be difference, of course, the first and the last regions. The number of filters per object, again, there are very few objects that have been observed above 40 filters, but we have a more or less nice coverage of, starting around 15 filters. So again, we can work with this. Continuing with the statistics, of course, one trait, since we have observed the first night, trace 1 and 3, and in the second and third nights, 1 and 3, 2 and 4, the first trait will be the one that has many more detections, well, first and third. And here we have the number of traits in which one object has been observed. It does not mean that it has been observed in all the filters, but at least in one filter, in one trait. Here I'm showing the statistics for some of the representing filters in the traits. This is the first, second, third, and fourth. As I mentioned before, the red trait has a smaller number of detections, as you can see here. Also comparing with the magnitude errors for each detection in these specific filters. Of course, as I said in the beginning, if we need to remove the sound contribution from the asteroid data that we recover with the telescope, we need to use either the sun spectrum, either solar stars that have been observed in the JPAS system, the JPAS filter system, or even in the images, which is not easy to find. So, first approach that has been done is using solar spectrum and convoluting this spectrum with the filter system of JPAS. By doing this, we obtain something that does not look very nice. These are the objects that have been observing the whole near ultraviolet range. So from around 50 that we expected, we have 30. And if you take a closer look, these are colored according to the traits. The fourth trait in red and the second tray in orange are always with an offset with respect to the other two. Of course. Why? Different nights of observation. This can be corrected. You can use the detections and try to remove this variation using the light curves, but it's not an easy task, and this is pending right now. This is a very, very, very preliminary correction, but again, improvements. And here's much clearer using the whole wavelength range that in the cases that we have the third and fourth trays, these parts appear shifted from the previous trays. Okay, but in any case, we have very good data here. Probably the red tray, the T4 we will probably have to apply some extra corrections due to the region that it is. But we can start to work with this data. We have 1.5 remaining nights to observe. So the statistic in principle will be large. So things to take away and that need to be. The spectral variation that we have seen, as I said, probably given or due to the light curve effects and the observational conditions, mainly to the variations due to the rotation of the asteroids. This needs to be corrected. We need to take observed solar stars, either in JPass, either in these images, to find the solar colors in this system, create how to say this, a better detection, right? The detection efficiency has been proved to be lower than expected in principle, so maybe we should try to increase the exposure times in the red tray, maybe also for the tray with the bluest filters. There's a taxonomic classification that will be created. Well, it's created for the J plus and J bar data, and that's another story. And it will be applied also here, of course, with expected tweaks. And depending on how this corrected data looks like, which I'm pretty confident that it will look much better. Maybe using or creating, asking for a legacy project to create, as I said in the beginning, the first near ultraviolet specific taxonomy. With that said, many thanks to Javiera and also the people in the OAJ, because I know that this is not simple to do. Thank you.
Thank you to you. We also know that JPCAM data is missing. So thanks for sharing the
I'm going to ask for another hard drive for this.
The questions for David? So I have questions, but well, are technical. Well, for example, the problem with you is that you are limited by the elevation of your fields, and then you can increase the exposure time or the number of images. But the problem is that then we are not going to be able to observe two trays.
I mean, we are not in the optimal conditions because the visible windows or the observational windows are between October and March, which are not the best.
And especially last year was, or this, no, the previous, this period from October to March was pretty bad, and probably we observed also with some thin clouds your project, because we wanted to you wanted, and you wanted to have some data at least to have something. So I guess that maybe it's not the well. Maybe conditions can be better, but we don't know.
Well, one more thing that I didn't say, that in the end we had to be more flexible with the observing conditions, because in the beginning, okay, we asked for time, whatever.
Yeah, can you, maybe you mentioned and I missed it. Can you expand on the fact that you were expecting 50 objects and you saw 15?
Observation.
So,
because in the beginning I said, okay, one scene, one zero air mass, 1.5.
I guess during the 5 years period, we will have all kinds of years. We will have good years and bad years, because this is cycle. There are cycles. Whether cycles. So in 5 years, I guess we will have all of type of years. But this last October-March period was one of the bad periods for weather conditions. So we needed to relax the conditions for some of them, especially this one that requires 5 hours of stable conditions, and we weren't able to do that. Okay. So, yes.
What object you actually into account? That, for instance, magnitude there. Did you have any cuts of this, or all detected?
All detected, of course. You need to trim that, because if you have objects observing just 3, 4, 5 filters, for what I want to do, it's not useful unless these 4 or 5 filters are scattered all the wavelength range, which probably won't happen. Only they.
Oh. Yeah, well, it dries quite fast. So for many objects, it's about 0.2.
Yeah.
Yes, you cannot really work with that.
I don't know. I need to think about it.
Anyway, okay, so challenge.
I know.
Okay.
But no one can say that we didn't try.
Yeah.
I'm still trying.
Well, you still have time until on October we will try again. Okay, so now it's lunch time. For those connected online, we see you at 3:30 the well time, so in 2 hours. Okay. And for those here, we see you at 3:30.
Sí, mandará el correo electrónico. Si quieres, vais con el pendrive y lo mandamos directamente. Porque te sea más fácil.
Hombre, si aquí todos estamos todos. Bueno, pero hablar en público. ¿Está grabando ya? Sí, estamos listos. So, please sit down. We are going to start. We will start the afternoon session. So we start with Borja and Llano. He's going to talk us about the Javalambre, Andromeda, and Triangulum legacy astrophysical survey.
All right. Okay. Well, thanks everyone. Hope you enjoy your lunch. Okay. Yeah. So yeah, as Javier mentioned, I'm going to talk about OAJ Atlas. It's a project. It's just being born, and I really hope I try to convince you it's a great survey for Javalambre facilities. Okay. So this is just bringing here the letter of intent that Andres and I we put together. So I'm just going to keep working, telling you about what is the plan we have and what we mentioned in the letter of intents. Well, first of all, I have been just several months already working on that, and I found that the community likes the project. So when I'm giving talks, I have been promoting this talk in different places like Core, Baltimore, Potsdam, China, Roma, SEA, in next month I'll show you about talk about that, and several more talks. I don't remember. I just put that together. So what I wanted to say here is that the community is finding this project very attractive. So during the coffee breaks or just after the talk, I have several colleagues that they have close to me showing interest. So I think we're getting momentum, which I really like it. And also, of course, thanks to Javier, Hector, Tony, and Javier, because they have been helping me and trying to put together this project, especially like understanding better how Alambre works. Everybody's welcome. And when you are here part of TEFCA, part of JPass, please, if you are interested on this, you are super welcome. Of course, benefits also comes with responsibilities. This is a big project. We need hands. We need to work together, and many people trying to put all this together. There are also a couple of publications working on. This is just the proceeding where I was giving a talk in Córdoba, and also I'm planning to put a scientific motivation paper that is just work in progress. Okay, well, let's talk about these two galaxies that they say the local group together with the Milky Way. Okay, they look quiet, they look peacefully quiet. I like this big field of view because you can see that M33 and M31 in the same image. Pandas show us that I mean, what we call it cannibals in galaxy formation. So you can see what a mess. Okay, all the stellar string cells that are going on right now in this system. So this is a little bit the idea. Probably many people here, especially those who are working on galaxy formation, is a big topic. It's a major goal in astrophysics, right? We have a theoretical framework. It's the lambda CDN, which predicts the importance of the role of mergers. We have seen that in the results from pandas. So in our own Milky Way, we have a perspective where we can just try to understand thanks to parallaxes, proper motions. We measure abundances through high resolution spectra, trying to put all these pieces together. That's what we call galactic archaeology. So this is a little bit the idea. Can we start to do this, what we call it galactic archaeology, but also in M31 and M33? People have been doing that already. Can we bring this JPCAM facility with the 56 narrow ones to try to start to keep going with this galactic archaeology concept, but in our neighbors, okay? So you can see that there is a large fraction of the halo that can be surveyed, limited to the scale coverage. We can get clean samples of the halo and these stars, and also identify the outer halo beyond 100 kiloparsecs. So this is a little bit the motivation, okay? Can we just use the facilities we have here to get a low resolution spectra of everything that is in the field of view to a given magnitude, okay? This is just to keep going with pandas. Pandas is going to be my kind of like my canon, right? To create this survey. So you can see here all the substructure that is there. They're just being in metallicity. And this is one of the things that they are doing with broadband photometry. With the broadband photometry, you have isochrones, so you can start to select what is metal rich and what is metal poor. With the spectrophotometry that we are going to get using JPCAM, we can get metallicities and hopefully alpha over iron for every single individual star who will be resolved. So I think this is powerful, okay? So, because pretty much all the surveys that they have been doing, mapping M31 and M33, they have been just using broadband photometry. As I said, pandas is going to be my reference, okay? So these are wide field mapping these two galaxies and the halos. They found a rich substructure as expected for the most massive galaxy in the local group, and also a myriad of satellites and halo tracers clusters. I will talk a little bit later about that. But there is limited information. There is limited spectral information. Okay, it's broadband imaging, so they are just like not able to get individual stellar parameters, metallicities, and alpha. So this is one of the main goals of what I'm trying to do this exercise. Also, we have a big field of view. So, okay, so this is the comparison between the field of view we have here in Alambre and the field of view that they were using for pandas. So we can go fast. Okay, we can go fast. So I will talk a little bit about the strategy because maybe we are not going to start to use the 56 colors. We will maybe focus on a very specific wavelength range to maximize and to start to get momentum with the survey. But that can be fast, okay? The field of view is incredible. I was making some numbers, like how much will take me to just cover the pandas area that is about 400 square degrees. So I was trying to integrate 300 seconds. This is a little bit of like the thing with the guider. We will have to be careful with that because we need to integrate probably more than 100 seconds to maximize the output of these surveys. So, okay, if I will have to cover the area of pandas using the 56 narrow bands, that will take around 200 clear mice. Those are the numbers, okay? This